Okay, so thank you all for attending. It's a Saturday afternoon, and we've very rarely done this on. Everyone can hear me, right?
Yes, yes.
All right. Okay. So we very rarely do this on an afternoon because normally we have our timings set from 10:30 to 1:30, and it's on a third Saturday. So we have retained our third Saturday slot, but we haven't done this in the morning. But I think it's okay to experiment with this sort of a timing as well. And given that it is online, we have again the flexibility of being able to record it, broadcast it, and being able to view it later on. Something that we were limited in our previous sessions. Now it's an interesting, that's a decent segue into our previous sessions, which is like Bangpypers has been around from 2005, started by Anand Pillai and a couple more awesome Pythonistas. And then it's completely volunteer driven, right? So um, people like Kresh Kumar and Chiller Anand, they all took up the helm to volunteer a couple of years later. And now recently, from the past 3 years, me, Anirudh and Ritesh have been uh, organizing meetups, workshops, and all of that. So that's what happens in a Bangpypers meetup. Where like typically we have a lot of Python work that we do at work, and maybe we have a lot of side projects as well, right? But all of this knowledge that we are accumulating in silos in our own sort of communities can possibly benefit people outside as well, and that is a small part of what we hope to accomplish with Bangpypers. And we've been reasonably successful so far, and it's not going to be possible in the future without the continued support, right? Like people need to come up to speak, like Mahesh and Kanishk have come forward to, and we also need like people to attend and tell people about the community so that everyone else can join as well, and like learn more and contribute more. So that's how it is, and we are always looking for volunteers to help us out, because the three of us are doing the best we can, but we'll always never say no to extra help, right? So that is the small pitch that I had from Bangpypers. Now we have two speakers today. We have Mahesh. He's going to talk about model deployment on Lambda, and then we have Kanishk talking about image classification, and he's got a nice use case for it. Very fun use case using Pokemon images. I'm sure no one is unfamiliar with the concept of Pokemon, but I'll let him talk about it in his second talk of the day. So with that, I think we'll move on to Mahesh presenting his first talk. So Mahesh, please, you are free to take over the screen.
Hey, yeah, can you hear me now?
Yeah, just one thing. So given that our we have just two talks, you're okay. You're welcome to take. I said 40 minutes, but you're welcome to take up to 45 to or even 1 hour if you want. Similarly for Kanishk as well. If yeah, or we can have question answers and all of that. And towards the end, after the two talks, we'll be having a small open house session where we can. I'll bring up a topic at that time. So yeah, thank you, Mahesh. We could hear you. Yeah, please
Yeah,
share.
sure. Thank you. Okay, thanks, Abhi. I think it's because of me. I think you rescheduled it. So because I had some prayer commitment which I was not able to avoid. Thanks for making that for me. Okay. Okay. So you'll be sharing the screen, or you want me to take control?
No, you can share. Have I not given you permission? Oh, I haven't. Okay, I've given you permission as well, so you can.
Okay. Okay. Let's see. Okay. So anyone can see my screen? I hope yes.
Yes, yes.
Yeah. Okay. Just a quick intro about me. So my name is Mahesh. So I work for Verizon. So I have around 13 years of experience. Mostly I worked in past 8 years. I've been working on the big data and Hadoop related technologies, and last 3-4 years predominantly working on the cloud, and especially the deployment part of the machine learning or the post-production support. So those kind of things I think we support internally for the Verizon applications. So so this talk is primarily about how to leverage the serverless platform, right? So I think we've been hearing about a lot of these terms, this Google App Engine, Lambda, or Azure. So how to leverage the serverless technologies to deploy the machine learning applications which we develop on the AWS. So that's a primary talk. So it's all about deploying your applications on AWS. So this talk, I'm not going to cover anything about the model development or anything, purely about once you have a model, how to put it on Lambda. So that's how that talk is going to be. So this is a quick agenda. We'll go. So what is the problem statement? Say, what are we trying to solve here? So maybe I'll give a quick intro about like what is the Lambda and what is the serverless and how the Lambda architecture works. There are certain challenges or limitations when it comes to Lambda. Maybe I'll explain you like what is that and how we are able to overcome those challenges with the Lambda. And you will see maybe I had one slide about like how is the performance between when it's deployed on EC2 and how is it when you have it on the Lambda and the cost wise and all those things. Okay, so when this effort started, I think maybe 1.5 years back. So when we had our first models developed in our team, right? So we are actually a pretty small team, so almost like 6 to 7 people we are. So when we developed a model, so that's the first model we developed. So we don't know how to deploy it. Okay, so we are exploring different options. So we tried, I think many hard Cloud Foundry. So that was one of the tool we use internally in Verizon. So we thought of deploying it on the Cloud Foundry, which is from Pivotal. That didn't work out well for us. Then we actually started with Flask, so the traditional approach, right? So we put it on a Flask, and we wrote a wrapper around it and put it on an engine server. So that's how we deployed our first model. And later we thought, okay, because internally, like in Verizon, we have the policies, right? We have to rebuild our AMIs and like rebuild our servers every 90 days. Okay, so that's like you have to freshly deploy everything again at every 90 days. So that overhead of maintenance is like causing us so much trouble. So we have to automate so many things. So that's like, then we thought, okay, let's explore some other tools which we can avoid all these kind of like easy to overheads, all those things. Then we were exploring the Dockers, Kubernetes, and then finally the Lambda. So Lambda worked pretty well for us because it's like the framework is simple. So once you have the model deployed on a Lambda, so the rest of the pieces are like static pieces. So we used load balancer, application load balancer for the REST API exposing. So we put it on a Lambda. So we have an application load balancer. We also have a wrapper called APG. So I don't know how many of you heard. APG is like an REST wrapper, sits on top of an ALB, which will handle us like some kind of securities, all these OWASP or threat checks or authentications, OAuth authentication, so spikers, everything the APG will take care. So our life was very easy. So we just had to create our Lambda. So developer has to just write his code, put it on Lambda. So ALB is a static part. You just need to add a new rule. Okay, if this is a rule, you go call this Lambda. So maybe I'll show all those things like how it is done. I'll try to show a demo for you guys. And any questions here? Maybe we'll make it like little interactive. So anyone have any questions here? Like, am I going so speed or slow?
I find the pace pretty fine, Mahesh. So
okay.
yeah.
Okay. So that's how it started. So we were able, I think now almost like we have around like 10 to 12 models running on this architecture. So the pretty successful architecture we have. So it's very stable and it provides the scalability internally. So we don't need to worry about, okay, suddenly some spike coming and how do we manage servers? So you don't need to have all those auto scaling, all those templates, cloud formations. You don't need to worry about anything. So Lambda just take care of your scalability, and we just need to tweak few things to make it more robust and more faster. So the cost wise, it's pretty cheap because you pay only for what you execute. It just like if you most of the times execute in milliseconds. All the predictions are like just milliseconds of time. So it's all pretty cheap. No need to manage any of your EC2 servers, completely managed by AWS. And we handle all the security and all with the using of APG framework. So if people don't have APG, so they can have their own kind of security in place. maybe they can have all those things written in Lambda itself to handle all those security parts. And it's highly scalable because Lambda will auto grow on its own. So that's the advantage. So coming to just a brief introduction, like what I think we already discussed, maybe just reiterating. So no servers to manage. So it's all like a function as a service, right? You just run your function on the AWS environment. So continuous scaling, no idle server time. So you're not wasting any of the server times. You just pay for what you use. So whenever your model is invoked by someone else, so you just pay for the execution time. And it's like pay per request, how much milliseconds or how much GB you use. And they have some calculations. So that's how it is. And it supports multiple languages. Ours is, I think, you're primarily concentrating on Python, but it supports other languages also like Java, Node.js, and C#, or PowerShell, Perl, PHP, I think. Competitors to Lambda, I think there are Azure Functions and Google App Engine. And the one advantage here we talk about Lambda, right? There is no boilerplate code which is related to AWS. It's like very minimal code which we use from the AWS SDK. Maybe the example I'm going to show you, there is no code from the AWS SDK. So it's like in the future, if you want to move it to either Flask or Kubernetes or Docker or something else, you don't need to worry much. So you don't need to reinvent or rewrite anything. So whatever is there, it's just like a normal code. So that's the one primary advantage here. And next, I think this is a high level architecture we have. So this is the complete flow of the pipeline. Okay. So when the guy consumer, he wants to invoke our API, so he has to authenticate. So we give them the credentials, which is provided by APG for us. It's like OAuth authentication. So OAuth is a famous security authentication, right? So we give them the keys and secret access codes. So they'll generate the authentication token. So they need to pass us the token. So APG will validate that whether this guy is the right guy or not. So there we avoided all this authentication issue. And it has so many beautiful features in APG, like you don't need to worry, spike arrest. So we can set it like, okay, man, my Lambda can handle only like 30 requests per second or like 1,100 per second. So you can have all those things so that it actually works for EC2 because it won't crash your servers. So it will stop it APG itself, like, okay, this is it won't let the request flow to the server and make it crash. And we have thread checks, like if someone, maybe it works like if it is mostly like if someone is trying to pass the queries, right? Maybe drop tables or SQL queries. So all those kind of checks or anything coming internally in the JSON, right, body. So all those things are handled by APG for us. Then once it goes all through the checks, it calls the load balancer. And the load balancer, we define the rules. Okay, if the user is asking for this method, okay, call this. It's kind of post methods, right? How we write in Flask / this method, this method, this method. So maybe I'll show it on the EC2 console. So like how it was driven. So this is the overall the flow and model. And we have the model Lambda. So that's the main Lambda. We have some like audits also. That's our separate Lambda. We can call it asynchronously. So it's just for our tracking purpose, which we store it in the S3 audit. It's all cheap. So there's no servers. Everything is on serverless. Any questions so far here? Anything, people? Any questions on this architecture or Lambda or anything? Before I dig deep into what is the Lambda and all those challenges.
Anyone can unmute themselves if they have a question, or if you want, you can put it on the chat. Nothing so far.
Okay, cool. Okay, this is actually the function lifecycle of the Lambda, right? So we have to package the code. So it's like simple Python. So what are dependencies you need? It's similar to maybe if you take any Java example, if you're from Java background. So you have all your jars packaged into one big jar, right? So all your dependencies and all you put into one jar. Similarly for Lambda also, you need to zip all your dependencies into one file. So if you are using scikit-learn, SciPy, or Pandas, NumPy, or even if you're using Keras or TensorFlow, so you need to package them, everything, and put it in a zip file and upload to S3 bucket. So that's the first step. So once you have the S3 bucket, you create a Lambda function. So create a Lambda function with your S3 bucket name. That's the zip file, and you give them the method name. So that's a file I'll show you. So once that is done, create a Lambda function. That part is done. So what will happen when you call the Lambda for the first time, right? So internally in the Lambda function, it will download your code from S3. It will create a virtual environment for you. It's similar to Docker technologies. So it will create a virtual environment for you. It will unzip your package. It will make everything ready. And it will execute the init function. So for example, in the Lambda, you have two stages. One is the Lambda handler. That's the main function. What are the code you written before that? It's called the initialization part. So that's where actually we preload all the connections or the model files. Heavy work and all actually we done in the init part to save some time for the real-time invocations. So invoke handler is the actual main method, that Lambda handler, and complete invocation. This is the first time it will do all this setup, like it will download code, environment, execution, all the init steps. But in the subsequent time, it will directly go and invoke your handler directly. So the first request will be always a slow. They call it as a cold start issue in Lambda. So that's a typical cold start issue. To avoid that cold start issue, I think we have some ways we can do that. We will explain you. But the first Lambda is always like a pretty slow. It will take at least, it depends on your package size. It might take maybe like 10 seconds sometimes. But subsequent all will be like milliseconds. So this is the function lifecycle of the Lambda. Okay. When it comes to Lambda, right, there are standard challenge actually. That's a 250 MB is unzipped. So your total packages include MB. That's the main limitation of the Lambda. So this is where we.
Mahesh, your audio cut off for the last 10 seconds. Can you please repeat?
Oh, sorry. You want me to go back the previous slide?
No, so same slide.
Okay.
What is the main limitation of Lambda? That part
okay, got it. So the main limitation, right? So when it comes to Lambda, right? So the total zip size what you give to the Amazon shouldn't exceed 250 MB. So all your packages or model files, everything. So there are certain ways we can do this. So we have an algorithm. I think we took it bits and pieces from so many GitLab projects and GitHub projects. So finally we come up with some solution, so which will reduce our package size. So we don't need all the so many stuff will be there. So when you install pandas or numpy analytica, right, it will install so many unnecessary packages inside it, like all these test files, some documentation, all those things are not needed. So this code, what we are going to show you, will remove all the stuff. So the default, like around 250 MB of size of the dependencies, it will bring it down to half actually. It will around like 110 MB is what you actually need. You don't need the rest of the stuff. It will remove all those things and make it very small. So that's the one algorithm actually we wrote it. So we took it bit from the GitHub projects, which are few open source things, and we finally try to achieve this. And there are other ways actually. So Lambda will give you a temp space of 500 MB, okay, that they'll provide you. So when they give a container, you have 500 MB of additional space provided /temp, right? So if you have any other files which are still exceeding 250, for example, deep learning packages, or this TensorFlow or XGBoost, these are like or around 110 MB, you can't do anything. You can't zip it because all are SO files, right? So in those cases, what we do is we put them into S3 bucket. We load them on the initialization phase. So we download these kind of additional dependencies and load it into the Lambda container and add it. In the Lambda, in the Python, the beauty, right, you can modify anything. So you can add your sys packages from anywhere, side packages, right? You can just say, okay, get from this location, temp location, add this also to your side packages. So it's like you can modify anything on your code. So that added advantage for us. So any additional files which are exceeding the 250 MB, we put it on S3, we download in the first warm phase and keep it ready. So the subsequent real-time invocations on all will be very fast. So that's the advantage. Maybe I'll show a demo like what we are doing so that you guys can get a clear idea like how we are doing all this stuff. And this is actually the way to handle the cold start, right? I told you the initial phase where it has to download the files and keep the environment ready. So what AWS does is we don't know actually the time. There are so many conditions, maybe 20 or 30 minutes only is your the VM will be active. After that, they'll destroy it. They'll destroy and give it to some other person or some other who is accessing the Lambda, right? So your Lambda won't be always alive. So they'll just keep it for some time. If they are not getting any requests for a certain duration of time, they'll destroy that. So one thing is you can poke the Lambdas in certain interval, so that always you will have certain lambdas always active, so that your request will be fast. Or as AWS provide you something called provisional concurrency. So what does is they will handle it for you. So they will always keep your lambda active, but they'll charge you additional thing. So I think almost like it depends on the number of parallel concurrencies you want to so you define it. So they'll put an additional charge for you. That will add some cost, but that depends on use case. If your use case doesn't need like millisecond and seconds kind of response, you can avoid it. But if you want those kind of things, you have this provisional concurrency. It will directly invoke start from the lambda handler. So all the initialization part, AWS will take care for you, so that you don't need to worry about it. So even like the good thing, right? So you can even write your parallel processing. If you have so many files to download from S3, we have one solution, one project where we need to download almost like 6 to 7 pickle files and almost like 3 to 4 CSVs. So those many files we need to download from S3, and so we simple Python pipe processing, right? So we wrote that code in the Lambda, so it's working pretty well. It's like saving almost like 2 to 3 additional seconds for us in the initialization phase. So that's how we were doing it. So you can play around with it like a normal Python. And this is the final slide, the comparison, right? We did it actually. So we put into the same thing on large machine, two T3 large machines and AWS Lambda. And we used low cost just to internal testing, right? We used a low cost as a framework to just see how it is performing the Lambda and all. So when you see, right, after a certain point of time, the EC2 is failing so much because that it was not able to take the load, but Lambda was able to grow. So it was able to scale it very dynamically. So here in the EC2 part, we don't have any auto scaling enabled. So after like 1,000 number of users and total requests are increasing, right, it was not able to take the load. It was so many failures are happening. But Lambda, the failures are like very less. So that's the main advantage. And if you see the cost, I think it's very less. So almost like 120 is for EC2, two large machines in to run. And the Lambda, it's around just $10. This is like overview, like what is the Lambda and how we are able to deploy. Maybe I'll show you a demo. Maybe that will give you a more idea like how you need to deploy it. So it's like a pretty short demo. Anything so far? Maybe or else we can discuss even after demo also. No questions? Either. Okay. I'll show.
So Mahesh, in this aspect, right, it would be nice if okay, actually you have all the elements there, I think. Okay, well, good. You have the model and you have the.
So I took some project from the GitHub, I think, which is already there. So I didn't build anything. I think I just tried to put it into Lambda and.
Okay, what I was going to say is like the life cycle. I know that you spoke. This talk was focused on just the deployment, but if you have like insights about just the life cycle itself, like how do you start and how did you get to that point, and then how you deployed it, that would be nice. I mean, like if that's not too much to ask.
Yeah. So that's what I'm doing. I don't know. So from morning, I think I was not able to log into the EC2s properly.
Okay.
Because I did because I cannot show the one on my office laptop, so I did set it up a new thing on my personal laptop.
Right.
Just to give me a minute, I'm not sure why it's not logging in. I'll just stop and start it again.
Okay.
Actually, I have a Lambda deployed. So just to for people, right? The flow goes like this. So you have an ELB. So ELB, I think everyone knows, right? So Amazon load balancer. So you can go and create your own load balancers. And then you have the listeners. So listener is the where you define all your rules, right? So here we can define the rules. I just define some sample thing. Like if my function is some lambda test, okay, forward it to this target. So like that, you can have a number of rules. So if I'm getting this function name, okay, give it to this. So you can define all your rules here. So once it matches, it goes to the lambda target, right? So this target is nothing but it will invoke the lambda function. So here you can define your target. What is the lambda function you need to invoke? We can even enable the health checks, but we don't need it actually. So it will again incur additional cost if you enable the health checks or not. So when a request comes to ELB, it will forward it to target. Target will invoke the lambda. So this is a lambda. So I think I just bought some test project here. So you just need to pass, like what is this? I think this is from Kardec example, I think. You just need to pass your input request.
What is the body of that request? Like what is it? Are they features? Are they what is it?
I think these are the inputs needed to determine whether they can sell their car or not. Yeah, there's a kind of features actually.
Okay.
So they need to pass all these things. Okay, whether I can sell my car or not. So I think this model will predict whether you can sell your car with this cost or not, something like that. I'm not sure
Okay.
what is that. So these are the features you need to pass. So once it will execute, the lambda will execute and tell you, okay, you can sell your car or something. That's a response we get. So this is, I think, a random forest model. Where am I? So yes, I think it's.
The IP is reachable, right?
Yeah, I made it open for after a few minutes back.
Okay. Also about the barrier to entry in terms of usage of this.
Mm-hmm.
If someone is this is probably a question I wanted to ask a bit later, but I'll ask now. Let's say someone is planning to do like a college project.
Mm-hmm.
So if you can tell about a little bit about what that would take in terms of using this, is this the best thing to use? Are there other options?
Actually, I don't know. It's maybe funny thing. Okay, so I actually did my recently my uh, MTech, right? MTech from the bits actually. So even actually this was the project idea. So I think I presented this in that. This was my project idea also,
Oh, cool.
where I presented this. I think this is the same project. So this is like a scalable, a generic machine learning deployment thing. So you can put it on the Lambda, right? Okay. I think we are good. We are inside. Okay. So, so this is the predict .py, which I got from some project. So from the GitHub. Okay, it's just a simple code. So they use sklearn or something. They load it. You just load your pickle. So this is the initialization part, right? Here you can write anything. So this is like one-time part. So here you can load your pickles. You can download the files from S3 and open your connection. This is a one-time for Lambda. So only the Lambda handler is what is invoked in the real time. So whenever you subsequent request now, it comes from Lambda handler. So whatever you write before the Lambda handler, it's all like an initialization part. So this is where we load all the pickles. I think this is only one pickle, but if you have more vectorizers or anything you have, so you can load all this stuff before your Lambda, like how you do it in the Flask also, right? So when you're enabling the Flask, you preload all your objects so that your request will serve very fast. So that's how you do. So you load all these things before this. Lambda handler is nothing but you get your, it's a simple code, like how you get in the Flask model, right? So you get your event. So the event, you'll pass it. You'll find what are those things you want. You just call your predict code, model.predict. It will give you something, then you return. So this is a standard boilerplate code you need to write for ELB. So only for ELB, you need to send it in this format, then only it will understand. Okay. Say Python. So it just runs, right? It just runs and gives you the code. Okay, now.
Can you hide that?
So yeah. So I already have an environment created. Okay.
I think Python 3.6 lib.
Yeah. Sorry, right? So these are all the things installed when I install like scikit-learn, pandas, numpy, nltk. So it will install all these things, right? If you see the size, it's around 245 MB. But for me, for my project execute, I don't need all these things. Okay, so I have a code which strips all these things, and this is what I read. I don't need all those additional stuff. So if you see the size, right, now it's just 126 MB, even including the model files, everything. So this executes perfectly well for me. So that's the beauty we wrote. Maybe I'll show the code quickly. Maybe I'll run the demo. It's just a 2 minutes demo, right? Now I cleared all my old things and all. And I don't need this. So it's a fresh start. So I have this build.sh file, which will create a new virtual environment again. So install all the packages, whatever I need. Then it will establish watches. So here we used something called iNotify. I don't know how many of you might be aware, right? iNotify is what will happen is it will, so when you're executing some code, right, it will mark like what and all directories or files it accessed, so that this code will take only those directories. So that is what is what internally happening. So we use that iNotify to find out what are the packages which are actually used by this and remove rest all the stuff. So now again it got created. So if you see inside, it's 150 MB. I think this is what the code does, right? So now you can just simply package it. So you have your environment ready. You just need to copy your environment to S3. You delete a function if it's already there, and you create a new function. You just need to give your region, your bucket name, your zip file name. If you have any VPC configuration subnets or security groups, what is the runtime and role? You need to define the role in the AWS. So this has an access to Lambda, EC2, CloudWatch, all those things. And this is your method name. Predict Lambda is a file. Lambda handler is, which is a main method. Timeout and memory. You need to define like how much memory you need. Based upon that, they'll charge you. So and how much timeout. So max is like, I think 15 minutes is currently the max timeout. And memory is like how much memory you want. So based upon that, they'll charge.
So is that in KBs? No.
That's MB, I think 3000 MB, so that's around 3 GB.
Okay, 3000. Okay.
So this goes and creates your model in the it might take sometimes I don't know in this environment I think it's taking some time to create. So once it create, you just need to go add it to your target, add it to your rule, and invoke it. That's how maybe you can. Maybe I'll execute my old one. Application.json, we have sample with me. Header. Okay, I think my IP is changed again. I don't know, something wrong, but that's the flow actually. So that's how you can see all your logs also. So the Lambda writes your logs to CloudWatch. So here you can come and see. I think there's something wrong with the code.
That's all right. I mean, like this demo
Yeah.
goes.
So yeah, that's the flow actually. So I think the script is also very simple. It's nothing. So if you see the script, right, you just need to create your HTML environment. So you install all your packages, what you need. Then this is the what we use. I notify wait, right? It will wait. It will check this directory. So what all the directories files used inside directory. So then you execute your function Python predict.py. Then it will write to this list. Okay, I notify wait list. So it will have all the files what access, and also we make sure we add all the py files because sometimes it might break. So whatever the .py files are available in this, I think we just add it to this pydep list, and then we club them both and remove all the pycs. That's a simple script actually.
So just a note to the general audience
So
is
this is how it
one,
creates.
one note. A lot of these things we take for granted because we've worked with them in the past. But if anyone has any doubt and if you want Mahesh to elaborate, please ask. It shouldn't be lost in the wind, right?
I have one architectural question for Mahesh.
Yeah.
Hi. So basically, usually your production workloads are you can't predict how long it will take. So why are you deploying it in Lambda? Rather, you want to go with some traditional like Kubernetes or EC2 itself, right?
Yeah, that's right. So I think the EC2 approach is what actually we initially had. So what is the problem with EC2 is, right, the loads are unpredictable sometimes, and So the auto scaling comes into play, and then we have to rehydrate the server side. So in our company, we have policy like we have to restart the server section. So they'll give a new AMIs every night because they put some patches and they have all those securities in place, right? So you have to create the servers. Also, you have to set up all these engines or unicorn, all those things, right? So you have to manage them. So when you have a pretty small team, so you need to have one guy who continuously monitors this for you, like whether your servers are up or engines is up or something. So all those additional things, apart from the cost, like cost is also right. So the EC2, if you're running 24/7, so the load is not constant. Okay, the load comes maybe like when the US time comes, it will maybe 4 to 5 hours is a peak load. The rest all is like a very standard load. Maybe you can have the auto scaling and you can bring down servers up and down. So all those things you need to have a complex thing, right? So when it comes to Lambda, you don't need to worry. Okay, you just put one Lambda there, it will scale. So if your requests are coming, so I think we get around like 25 to 30,000 requests per day with multiple functions on the Lambda. So it is handling pretty well. And Kubernetes is actually one right approach. So I think the alternative to Lambda is like Kubernetes. I think that's, but when we started, we don't have the proper Kubernetes setup and all those headache. I think now it is there. Kubernetes is one good optional for this, right? So that you can define your pods, it will scale also.
Right.
That's right. That's the right way.
And you can do serverless on Kubernetes also.
That's right.
And one other thing was, what happens if the workload exceeds your Lambda time? What happens to that job?
Yeah, so that's 15 minutes, right? So because most of them are like microservices or predictions, right? So ideally, we can't expect them to run more than a second. That's the ideal way, right? But that's right. So if you have more than 15 seconds, you can do it. Actually, we play around with so much actually with the Lambda. We actually mimic the scoop functionality. So you are aware of scoop, right? The Hadoop scoop.
No, I'm new to that department of big data. Yeah.
Okay. What Scoop does is, right, Scoop is one tool which is used primarily for extracting the data from these databases like Oracle or Teradata. So that's the main tool we use in the big data to pull the data. It works on parallel processing. So it spans like maybe 10 or 100 or whatever you define, right? So that same functionality actually you can execute it on Lambda. So you can span the Lambdas as many as you want. So you have one good main Lambda, you span it. So you have a context object actually. So when you see the code, right, there is something called context object, which actually is very important, but we usually ignore. This will tell you how much time is spending in the Lambda, even while running, right? That will tell you dynamically how much time is spending for your Lambda, how much memory it's utilizing. So all those things are there. So you can use the context object. If you feel that your Lambda is exceeding, you can actually invoke one more Lambda and pass all this data to that Lambda. So you can play around, but it all comes with the complexities and the architecture, right? But for real-time prediction, I think this is working pretty good for us. Only challenge is maybe if we have pretty huge models, like your models are like GBs and all, it won't work. This is like light models, that's good.
Yes, because see, in production, if it is a new data set altogether, it will take minutes. And that way Lambda will not scale for you.
No, this is not for training. Training, you cannot even use it.
Exactly.
For real-time prediction,
exactly,
you can use it. That too, even if your pickles altogether don't exceed 200 or 300 MB. Leave the package size. Package size maybe you can handle. Pickle size also maybe shouldn't exceed more than 300 MB. That's the limit. You can't avoid more than.
And see, that is why, you see, what you're doing is perfectly fine. Actually, Lambda is one of the hottest tech thing which is going on now. I'm not denying that. I'm not denying that. It's state of the art. It is not something which you're using some traditional architecture. You're using a latest architecture. But the only thing what I'm saying is you're bound by those constraints of what Lambda is going to give you.
That's right. So whatever the cost benefit is giving, actually it has so many constraints coming with this.
Correct. So that's why I'm saying Kubernetes is one of the best thing even for machine learning.
That's right.
Because that way you have an end-to-end control of your infrastructure, your execution time, your everything, your model,
that's right.
everything you have, and also you can scale it also. So again, what happens is, see, another advantage of Kubernetes is you can replicate that in any cloud. Now, Lambda, you have to do it only in AWS. Whereas if you do it in Kubernetes, right, you can easily shift to GCP, Azure, whichever cloud you want, something like that.
Yeah, but I think that's right. You're absolutely right. So the Kubernetes is actually the right way, other than the traditional Flask or Unicorn engines way, right? So this Lambda is primarily for very small teams, and you don't have resources, and you just don't have money. So it's like
how many jobs you run in a day?
It's around like we have around like 10 to 12 models running. I think we get around like 30,000 requests. I think it is fine. It is pretty fine for us.
Okay. And one other thing is that the one which you have highlighted, right? The counter, the context something. You can also use a decorator for that, right? To find out how much is the execution time or something.
Yeah.
I don't think the context is. I mean, that's
context
not
has that features.
manager,
so it has the properties. It will tell you like how much time is spending from the Lambda point of view. All those, like, it's all related to Lambda context.
Yeah, Abhiram was trying to say something. Yeah,
it's a state manager, right? It's not alone in its counting property. It is more than that, right?
Okay.
Yeah, you have a lot of attributes associated with the context. Context dot counter is something that will probably tell you, right?
Okay.
Yes.
Okay. Cool. Thanks.
Good. Anyone else have any questions? I think that's it pretty much I have. If anyone want to discuss anything more, maybe I can.
I think this was pretty good actually. There was one thing that I wanted to ask. Can you go back to the UI? There was the logs there.
Yeah.
Yeah. So there.
It will write all the logs. Like CloudWatch, right? So all the Lambda logs will be written here.
Okay. All right. Well, what is the cleanup policy on this? Like, is it automatic or do you do it manually? What is there rules?
We need to define all these rules and all. So all these logs, I think it's forever. Okay. So I think it comes with, I think the account, they'll give this much, I think logs and all, but we can have our own jobs to do all this cleanup. I think Lambda will do. So Lambda, it's not only for machine learning, right? So it's like a pretty powerful tool when you're using AWS as a main cloud, right? So you can control any of your components on the AWS with the Lambda. So you can start your EC2s, run your EC2s, clean up your logs, all those things you can do.
Right. And does that add to the cost in terms of like how much it is occupying? Does it
this log memory, right? Yeah, log size and all will be added to your cost, obviously.
Because
we charge you for everything.
In our use case, we tend to have a lot of logs in a day. Typically, sometimes it goes up to GBs. So I was wondering if the cleanup policy needs to be a little bit more robust in case we use this at any point of time.
Yeah. So yeah, you need to clean the logs, but AWS, I think whatever you put, they put money on it.
Right. But you're saying even with all of that money, it is still more economical than having to pay.
That's right. So when you see this, I think it's because the number of requests or where I have it. You're right. This is what they compare. Like almost like we use 1 GB and for 3 seconds. 3 seconds is like also pretty delay time when you're talking about real time, right? Ideally, it should be less than a second.
Right.
Okay. And if you take
nice.
666, it's just $10, right? But additionally, you'll have the ALB cost, S3 cost. That's ALB anyway standard, right? Even if you're using EC2, you have to maintain an ALB. So ALB is a constant.
Right.
ALB and S3 cost. S3 is cheap, but only thing is Lambda, when you have limited things, I think it's a good one if you have small models and all. But if you are going for pretty heavy models, heavyweight models, like all these deep learning language models and all, so that time you might have some struggle. So that time I think you need to go for either Kubernetes or traditional engines or unicorn model.
Right. Okay. Cool. I think we are fine, and we are also on time. I think it's extended a little bit, but we have allowed for that because we have only 2 talks today. Anyway, if anyone else has any questions for Mahesh, now is the time. I mean, now it's not the only time. You can ask questions at the end of the second talk as well. If not, thank you, Mahesh. This was really nice, and like I think it's given people a taste of how it is to deploy models on Lambda and the entire flow as well, right? Um, so that is really useful, and I assume that these slides will be made available later on for. Uh,
Yeah, I think this is an open slide. I think you have it, right? You have a copy, right?
Yeah, I have it, but I was asking, can I publish it?
Yeah.
Okay.
Yeah,
Thank
I
you.
copied few things from the AWS because I don't have time. So
Fair enough. I mean, that is canon, right? You have to copy from the source to actually give it. That's fine. But thank you again for a nice talk, and we will be we have a recording of this. We will be publishing it and stuff.
Sure. Thanks, Abhi.
So thank you. So we'll take like a small 2 to 3 minute break, and then we'll come back with our second speaker, Kanishk, who's going to talk about image classification using Python. So that's what it is. It's 5:56. We'll come back at 16 o'clock, 4 o'clock. In the meantime, this meetup will be we'll still have this call open, right? So if anyone has any topics to talk about, if they want to say anything about how they're using Python, or if they have comments or questions on Mahesh's talk, please go ahead. Feel free to unmute yourself or put it in the chat. And if you have any questions for us, me, Ritesh, and Anirudh.
This APIG was acquired by Google, right?
Yes, PG was acquired by Google. I think it was
Yeah.
Yeah. So you're using Google on AWS, right? Kind of.
Yeah, the
Kind
Epic
of.
has their own actually very good advantages, right? So it's actually go-to standard for us. Like it will give you the beautiful, like you don't need to worry, right? As a developers, you don't need to handle all those thread checks, authentication.
Yeah.
Even Kubernetes, I think we use the same. So Kubernetes also, the request has to go through RPG. So RPG is a first level, then only it goes through either Kubernetes or anything.
So who's managing the Kubernetes part?
So it's like it's managed at org level for us usually.
Okay.
Because that's one pretty headache, right? So Kubernetes is one complex architecture to build actually.
Yeah. And
I think now Amazon has their own. I think they bought it, right? I think they have their own Kubernetes platform.
Everybody has got it. So everybody gives you a managed version of it.
Yeah.
And what do you run on that?
Which one?
On Kubernetes, what do you run? Like, what is the workload on Kubernetes?
No, Kubernetes, I think we don't have any proper workload. Now we're just trying out now POCs because we have some large models, so which we are not able to put it on Lambda. So that's where I think we are exploring the Kubernetes. We're just doing the POCs now with all those pods and Docker files, everything.
There is a thing called Kubeflow.
Yeah, that's right.
That will help you build your.
In terms of questions about Kubernetes, there is someone called Nabarun here on our roster, I think, and he is one of the contributors to Kubernetes. So if you have any questions about that, Nabarun, maybe you can pitch in as well.
So what I was saying was Kubeflow helps you build that models and in Kubernetes, and also you have Kubeless, which is
it's similar to serverless, right?
Which is exactly. So it's but you are right. I mean, it's a whole layer of complexity that you will have to cater to, apart from doing your regular coding and everything.
That's right. That's why I think this works. This is initially working for us because we don't need to worry all the headaches. Now someone else is maintaining that. Now that's why we are trying that.
Your Verizon Bangalore,
Chennai.
Oh, you know Saro?
So no idea.
Okay. He was working there, but
Okay.
he left now, I think.
Okay, so it is 4 o'clock. I apologize for the interruption, but
No,
it was
fine. I was just waiting for the next speaker to come.
right. So our next speaker is Kanishk, and he's here. So Kanishk, maybe you can unmute yourself and you can start sharing and talk a little bit about yourself.
Yeah. Hey guys, I'll just first do the setup. Phone, whiteboard, okay, screen one, I guess. Okay, this doesn't share the, okay. Uh, is my screen visible? You guys are able to see the slides part, right?
Yes,
Yeah. So these are, and the tabs are also working just fine, right?
all good. You can see all of them.
I'll need a sketchpad. How do I share? Okay, I'll need.
You can open canvas.io or
No, I have a sketchpad, but it's like offline sketch, Autodesk sketchbook I'm using. Okay, I'll try to open that tab as well. Just give me a second. Canvas.io.
yes.
It's not showing option of
I think I
sharing the whole screen directly.
canva.io. Just omit the S or even sketch.io. I think.
Sketch.io, no, that's not it. So I'll see when once I need to move to Sketchpad, I think I'll reshare or something like that. It's not allowing me to share the whole screen, but one tab at a time. Okay.
No,
Yeah.
when you shared the sketch, I could see it.
But it's in the browse tab. You are not able to see the actual sketchbook,
Okay.
right? So that's on my it's a Autodesk installer on my Windows desktop app that I'm not able to share directly. Okay, yeah, cool. We'll see once as we move forward. So a bit about myself. So I'm a 2015 graduate from IIT Kanpur, and after that I've been working in Bangalore for past 5 years, primarily on image classification and machine learning. Now I'm working at O9 Solutions. I'm colleague with Abhiram here. So I joined O9 recently. I got to know, and then I thought, like, why not just I got, get the opportunity to present. So here I am presenting with this thing. So the topic I wanted to cover about is image classification. Why I picked this topic? Primarily, this is where I basically started my machine learning journey from. This was like the very first problems I solved. I didn't know anything at the point when I didn't know anything about machine learning or any mathematics involved. Generally, people start from say SVM, linear regression problems. But for me, this was the like very first project as a summer project I started working on, and that's when I started to like take interest. Okay, machine learning is pretty cool. It was a few years later when you start to do the complicated maths and go into like the old core algorithms, CRFs and all, and then you realize, okay, that's not pretty cool part about the machine learning. That's pretty complicated, but yeah, still it's fun to do this machine learning stuff. And when it comes to image classification, when you can see whatever you are trying to do, whether you are trying to do classification, segmentation things, like trying to crop, like detect some object, there's an image given to you, you're trying to detect a car in that, trying to detect a person in that image, trying to do all sorts of like whether tell, okay, this guy is Abhiram, this guy is Kanish, this guy is X. That feels pretty cool once you are like successfully achieve those results after like spending some time developing models. So let's start with the presentation. So this will be the agenda. So this is like a very generic overview. There will be some extra slides and some details I have added to and fro. So very first thing that we'll cover basically as the topic says, image classification. So what exactly is image classification? Why we need image classification and how we do it. So image classification, that's like a very standard definition, Wikipedia copy pasted definition, assigning pixels in the image to categories or classes of interest. So here I have like tried to like pixelate the image. So when you are in a computer, say when you are in person, you can tell, okay, this guy is a dog, this is a cat, but you don't actually pixelate. You just learn features internally and implicitly ki, okay, if there is like a pointed nose outside, it's a dog. If it's like a flat face, it's a cat. Although if the you may not be able to tell with the looking just at the body, but like some features, distinguishing features, you start to learn. But for our computer, for our system, it eventually sees image as a pixel. So eventually what we'll be doing is like we'll just feed pixels, we'll try to do some magic voodoo over those pixels, those numbers that it will be seeing, and we'll try to like make the model say, okay, this combination of numbers is a dog, this combination of numbers applied some transformations is a cat. So that's our image classification journey. Just a second. Sorry. So, oh, sorry. Yeah. So here you can see like it's a very easy example. You might think like, okay, it's a Pikachu and it's a Charmander. Like it's like a very differentiable images for a person as well, and this data set will be simple enough for the computer as well, because it's like a colors are completely different, shapes are different, there are like clearly distinguishing features. But there can be problems that are like, hard to classify. Say even like humans get confused, like Will Ferrell, Chad Smith, those two guys I always confuse like who is who if they just try to do some different makeup and all. So but we can train our computers to exactly classify, like remove those errors as well, like they don't confuse at all, whoever whatever of those two people it is. So now you going to why. So this is like a very vast industry now. Whatever social media, whatever place you go, like your phones, your computer, cars, everywhere you will be seeing image classification implemented. Automated, like when you use Google Photos, Facebook tagging feature, you see like you upload a photo, you don't tag someone, Facebook will automatically suggest, okay, it's apparently this person, do you want to tag him or her? How does Facebook know? You didn't give any information. It's running internally this image recognition. Google Photos, it initially it asks for some training for you. Okay, just tag few persons in those people, like this is person X, this is person Y, and then you start uploading more photos. It will automatically assign and automatically start sharing, automatic sharing feature that we use. Then it comes like image search. It's like a pretty standard tool everyone might have used for Google image search. Or for shopping, you just take a snap, upload, it will show you similar results. Again, like you upload a photo of purse, the image you uploaded, the system will recognize, okay, it's a purse, it's green in color, let's show something similar that has been tagged similarly. Face recognition, you are putting your face, it will generate, do all sorts of key point detection on your face quickly, like with the all the deep learning models running there. And then okay, say okay, this person is someone X, and X is authorized to use this phone, just log him in. Healthcare industry and say vegetation industry that I have not mentioned, they are like pretty deep and like pretty serious industry, and they are starting to rely on image processing, because even sometimes persons cannot exactly tell, like only a like a very experienced doctor may be able to tell, like recognize these cancer cells and all. But you once you start training these models, and people are starting to use image recognition in pathology, for cancer cell detections, for the cures, combination, and all sorts of health predictions. Automobile industry, everyone talks about now self-driven cars these days. Okay, there will be cars driving themselves, but when you think about it, what's exactly happening, it starts at this is like the very first step. If your image classification models that you put in place, they are bad, whatever you do, you can't make a self-driving car until unless you fix your image classification models. So that's how this image classification problem, it's such importance of this image classification problem in the real world as well. So it's like a, and you might have heard like whenever it's you start with image processing normal, even in courses and all, people generally now start to teach with MNIST data sets, which is like a digits data set, 0 to 10 digits labeled and collected from postcards and everywhere. That becomes like a hello word of this image classification and image processing industry now. And in some sense, looking at this toughness, when it's now people are trying to do with like vegetation requirement in the field, and security cams, whatever we have on the metros and all, like doing automatic crowd detection there, uh, person detection on those, on that sort of data set, where you see like it's, you might have seen some footages there, I don't know, even less than 360p of resolution, trying to do face recognition from there. There was this Chinese startup who has I think last year they gave an interview that they have every person's database in some cities, and they can tell which person is which. looking from a like a normal security footage, generic security footage taken from like either from this signals, traffic light signals from a metro. So moving forward, so now is the third part. How do we do image classification? So in image classification, it's like a very generally, if you think about it, like classification, what as I mentioned in the very first slide, uh, typically you give take some numbers, do some voodoo with the numbers, feed it to the computer, and like start telling, okay, first few iterations you tell the computer, okay, see this image, these the combination of numbers is some person X or some dog. Computer will internalize that concept. Okay, this combination of numbers is called a dog. Some X different combination numbers is called a cat. So similarly, the image classification problem is approached. First, we get basically image classification problem. Our starting point is an image. Uh, so what we do with the image, very first iteration in a standard pipeline that you follow, you get 100 images, you have to split it. So because you can't train on all 100 images, you need some images to benchmark your models as well. So you split it. That's a standard ratio that gets followed everywhere in academia or in the industry. Like do it a 60-20-20. So 60% you will be training on, 20% you will be using to fine tune your model, and this 20% is like a completely last stage data set that you keep aside until unless you are sure, okay, this is the model I finally want to push into production or finally want to use after all your experimentation done. Second is data augmentation, class balancing. Say you are building some sort of building versus tree classifier simply in a city. So in a city, you will get like 80% of the images, and you send someone out, he like just take the images around the city. What you will get, 80% of the images will be of a building, 20% will be of some like trees or like natural habitat. So you need to like tell, and if you start training, the computer will mostly see, okay, this is a 80% of the time it is gonna see a building. It There is a chance that computer will get biased, okay, everything is like a building. And if it's not a balanced data, say again your test data is say similarly like that, 80% of is it a building, 20% is a class, a tree. For the computer, easiest thing, just call everything as a building. You will get a better numbers, better accuracy and all. So that's why we need to do like class balancing, and then data augmentation. There is a data augmentation is like doing some adding some same image, you do like a different crops, or you do some sorts of color balancing, some changing of color. I'll cover that part in detail when I move to that image processing exactly, but this is like a generic definition I'm giving right now. Then second step, once you have done all the data balancing, you have done all the data preparation, you define your model, what you're going to train with that data that you have covered prepared so far. That can be as simple as VM support vector machine, that can be like a neural network that you want to train, that can be just a simply Bayesian classifier, that can be even can be a simply a coin flip. Okay, I see an image, I'll do a like a random 0, 2, whatever it says 0, I'll call it building. If it says 1, I'll call it a tree. Anything that you want to train on that. Then comes the part of training the model. That's where basically it's like a iterative process that we are stepping into. Whatever model architecture params you have defined, you train it. And then fourth and third and fourth are basically steps that you say go hand in hand. You train a model, you evaluate this performance with your performance metrics you might have defined. You see, okay, this performance is not good enough for me. You update your parameters. You got to see, or you change your some data prep that you have done. Update parameter, train a new model. You get a new model, you reevaluate your KPIs. It might be better than the previous one. It might be worse than the previous one. Based on these combinations, you can basically keep experimenting. You spend time on experimenting, and then eventually after some good brain work, good innovation that you might have put into, some innovative ideas that you might have put into, and some good luck, so you might finally arrive at the model that you actually can use for your like testing purposes, or push it into a production if you're working. So, and training, it's like a so yeah, that's three ways. This is like a pipeline, same that is mentioned as a numbers. You get your data, do a split, train data, you define your pre-processing, do feature extraction. Features, there are like multiple ways. You can just look at image, you want to see, okay, I'll just some manually handcrafting features, or there are standard features that are defined, shift feature, hog features. I'll cover features as well. Or you can directly use a convolution networks that automatically get your features out. Then there will be a model that you have defined that I was talking about. Then again, this part is like a loss, update, train, get a performance, reevaluate. Once you arrive at a model, you get your test data out, apply the same pre-processing that you have defined, and report the final performance. So now moving till this point, does anyone have any questions so far? How can I see?
I have some general questions. I
Yeah.
hope it's not too simple for you. Um, I mean, I'm basically new to this uh, image classification. So,
Yeah,
but
please
I
go
need
ahead.
some idea about what are the software that you use for things like setting up the CNN feature extraction and all that. How would
Yes,
you?
that I'll cover later as well. But yeah, so see, there are in Python. So since it's about Python, in Python there are image processing has been pretty much developed module. So there is a sklearn library that you can use, and sklearn and OpenCV. You can do the experimentation. You can do. There are already these shift features, hog features. Things are defined. If you want to do directly handcrafted, then OpenCV is a way to go. You can just put in your image as a numpy array, and then you can just keep on visualizing and do manual extraction, whatever you want to do with that. And if you want to go ahead with the convolution neural networks path, there are like primarily there are three libraries: Cafe, PyTorch, and TensorFlow. I'll be covering the PyTorch here. TensorFlow and Cafe also, there are all alternatives depending on your requirement, depending on your comfort with it. You can pick any of it.
Okay, thank you. If you're covering that, that'll be good. Thank you.
Yes. Uh, Abir, I'm just trying to get a okay chat. If anyone has questions, you can put it in chat as well. Or if the pace is fine by you, you do want me to slow down or speed up anything?
I
Any
think the
doubt
basic,
or any? Yeah.
I think the basic is very good. Like I'm used to you speaking way faster. This is perfect. Uh, also, if there are any questions on the chat, don't worry about it. I will read them out to you by voice uninterrupted. So
Sure.
go ahead.
Sure. Just a note by the way. So I would say, please keep asking questions. So this is a topic. If you the part that I have covered is not clear to anyone, you will struggle with the part that's gonna come in the next slide. So please keep your doubts clear as we move forward. I'll try to, with the numerical examples, with everything, I'll try to cover all your doubts. So you can throw in any doubt that you have. Don't hesitate at all, anyone. So now let's talk about our data set that we are gonna do. So yeah, that I think you might have already gotten that idea. We'll be working with a Pokemon data set. So this is the data set that's been put on Kaggle. So that's not a very cleaned data set. So I just downloaded and cleaned it out. And for the limitations of the OS and go collaborate GPU limitations, I had to, like, I can't do on, I think there are around 120 plus Pokemons classes available. So I just randomly picked 10 classes which had like some good number of images. Some of them had only 10 images overall. Some of them had 50, 60 plus. So I just picked which had overall 50 plus, and then did a 60, 40%. Now, if you any doubt, like, where is the test set in this? I didn't create a test set because I don't have to push a model finally into production. So I'll be using simply the validation data set for fine tuning and as well as for reporting for my purpose. So let's look at the data set here. Uh, Now the collab is visible now, right?
Yes.
Yeah. So see, whoever is not familiar with Google Colab, it's a pretty cool thing these Google guys have provided to us. It's like a exact same interface to a Jupyter notebook, but you can use GPUs, TPUs, and other features. You can store or you can load your Google Drive data. You can load your store your code directly into GitHub. So they have it's like a free tool anyone can use for any purpose, and it's like like promoted for the research purposes. There are no regulations around for industrial and like for a big business purpose, but for at least for research purpose it's completely free. It provides you GPU access as well, because GPU access in this age everyone starts to work on this deep learning thing. GPUs are becoming costly. They are not cheap to get your hands on whatever GPUs want. They are all limited, but Google Colab is like a free GPU for at least for student purpose and for demo purpose if you want to create. So these are the resources available. This is like a standard module provided by Colab to give you some idea into how much is the resources available. So one thing I want to mention is I'm not gonna run again because as I mentioned, due to resource limitations, sometimes these blocks crash out, and so I have just done a one iteration when it was up and running. So I have just kept those results stored. So whatever results are there, I can't run because it might start crashing or it might get stuck. So I'll just go with that pace. So these are the resources. If you see like generic RAM free is 12 GB, it's a pretty good RAM available. GPU RAM for 8 GB. But it's like a subjective to the availability. Sometimes it fluctuates. So that's why I've tried to do all training on CPU for this purpose. So this is our data that we have. If you see like these are 10 classes, I'm loading directly from, you can mount the Google Drive. Horsey, there are 32 images in the training for this class, 22 in validation. Mankey, 32, around like 32 images in training part, 24 images in the validation or test part for us. And these are the images if you want to have a look at, like one for each Horsey. So these are not exactly from the like anime or cartoon. These are maybe some hand-drawn portraits from like these playing cards, tarot cards, from like goodies and everywhere. It's like a collaboration of all such sorts of images. So it's not a standard image, but yeah, these are your 10 classes that we will be working with currently. So that's good. The data good part is good enough, right? Again, I'm asking the same question. Till this data and the generic overview of pipeline, everything is good, right? So yeah, I'll move ahead if there is no doubt. So now what we will be looking at basically, primarily for class, when you talk about classification, primarily people talk about supervised classification, supervised learning. So whoever is not familiar with machine learning, there are like two parts: supervised, three basically: supervised, unsupervised, and reinforcement. So in our context, mostly supervised and unsupervised are more important things. So supervised is basically where you have a data, you have a answer, you have a question, you have an answer available to as well for the computer to say, okay, this is the exact answer, you need to learn this mapping. In unsupervised, you don't have those answer, or what we call in our standard terminology label or target. So just computer internally learns, okay, this set of data is different from this set of data, but it doesn't know which these two sets of data are. It will group, say if you're doing simply, again going back to our dog and cat, it will say, okay, this is a group for some species S, this is a group for some species Y, but it won't know which one is a dog or which one is a cat. But it will start to learn, okay, these two are separate species at least. In supervised, you also provide them with a label. Okay, this species is called dog, this species is called cat. So model will learn that thing as well. Okay, this is a dog, this is a cat. So we'll be covering supervised classification in this part. Because this is more of a standard. Unsupervised, it comes with more new definitions that might be too much for the time constraint and all. So we'll be focusing on the supervised part. So just a brief intro of this SVM we'll be covering is, so SVM, as the name goes, it's a support vector machine. Why I'm covering these two, basically I'm going to cover SVM and I'm going to cover convolutional neural networks. So convolutional neural networks is something that's state of the art, so that we should get a gist of what those are, what's that whole magic is. And SVM is like an entry point for machine learning, sort of. Everyone who gets into machine learning has to learn about SVM, what is this thing is. And it's like a super cool thing someone has whoever started innovated it. Like it was, I think, designed like 50-60 years back, but it's still in use till this date. And you will see SVMs even in production. Every industry is going to use SVM at some point for something. So SVM, support vector machine, as goes, it's like a maximum margin classifier. What we try to do, say given your set of points red, one and green ones, what we try to find a line that basically separates them. But if you see in this width, right, between two dotted lines, any line can be your separator for this simple data set. But what we try to do is like put this separating line in such a way that it's the distance between from the red dots and from this left dots, it is optimized. And since see, we know like these are two dotted lines, we know like we can't optimize for all points because there will be outliers coming in, there will be all sorts of. So we try to find the nearest points, like these first we try to define these dotted line 1 points, which we call support vectors. These are the support vectors in sense these are the supporting the distance, like supporting the optimization parameter for this group of green data points, the green dotted line passing through this point. This for the red data set, these 2 points are like defining your like how much you're controlling your optimizing parameters for this hyperplane. And this black, the hard line, becomes your decision boundary. So if it's a 2D data set, it's gonna be a simple line. If it's a 3D data set, it will be like a plane. If it's a 4D data set, you keep on increasing your dimension. You can go in any dimension. You can change like if you are in n dimension, there will be a plane of n-1 dimension. That will be your separate. That can be your hyperplane. But but a limitation is this is a, if you all can see, it's like a linear classifier, right? You can't separate it. If say there is an overlap of these points, say there's like a green points are put in center and red points are around it, linear classifier simply can't separate it. Or other is like it's a binary classifier as well, one at a time. So you can't, if there is a 3 class, you can't find a line that can separate 3 classes, right? In a 2D plane, a single line can mostly divide the whole plane into 2 classes maximum. So there are strategies put into place. So first I'll be covering this binary classifier part. So that's where I need to use your sketchpad. I need to check how to share this. Share, new share. Yeah, sure, got it. Sure. You guys can see it right now, the share as well?
Yes.
Yeah. So now see, this is a 3 class classifier. So I would like people to like unmute your mind and like, how do you think this classifier is gonna work for this? For a 2 class, this is the class, you draw a line. For these 3 classes, black, purple, red and blue, how do you think like which line can separate? Like how should we approach this problem? There's a hint already on the screen. There is a name, but you can evaluate like how do you think we can approach this?
One line won't suffice, right?
Yes, one line won't suffice. So what can we do now for this?
You have 2 intersecting planes maybe.
Okay, so there is no, yeah, not exactly. So what we do is a little bit very obvious trick that we do. It sounds obvious, but that's how also it works. So what we'll do, we'll learn different number of classifiers. So there are 2 techniques, one versus all and one versus one. So say we eventually want a whole model to that does a classifier, right? So what we'll try to do is, say first we'll cover one versus one combination. One versus one is you randomly pick 2 classes and learn a SVM for these 2 classes. For red and black, red and black classes, this is sorry, let me just take a green different color. For red and black, this becomes your classifier. Now you will take another black and blue, this becomes your classifier. Now you will pick red and blue. It's not exactly intersecting, it can be anything. It's not exactly intersecting, it does not have to be intersecting. This becomes your classifier, say maximum margin. If the say red is somewhere else, it might become your classifier. So this whole SVM that you're finally gonna train using this one versus one strategy, yeah, it's gonna be a combination of multiple classifiers. So when you pass these set of data sets, it will internally run these 3 separate decision boundary classifiers for you. So it's eventually gonna be, it's a n classes, you're gonna internally train NC2 classifiers. Now this is one versus one strategy that we use to accommodate for multiple classes. Now it's a one versus all. One versus all, and next suggests this black one becomes yours. So now it's n classes, you will be training n classes internally. This for first iteration, this black will become as positive and red and blue will go into a negative class. For second iteration, red will become positive, black and blue will become your negative class. For the third iteration, blue will become a positive class, red and black will become your negative class. Now again, these are 3 classifiers optimized independently, but when you are gonna do your testing, when you're gonna do like evaluation, run your model, internally all these 3 classifiers will run for each point, and whatever gets the maximum votes. So it's like and then Each classifier, it's like after that, once you have results, say n results in this case and nc2 results in the other case, you do voting. Just like decision tree and all, you just do a voting. Whoever said, okay, this belongs to this class, who gets majority votes, you just push it. Okay, this is the final class. So that takes care of our binary problem. Now coming back to linear problem, how do you solve the linear problem? So that's where very ingenious and cool idea, kernels. Kernels say, see, like this is an image that I was talking about. Points in red in center, blue. Now you're looking it into 2D, and blue is around it. Clearly, there is no way a line can. It's a 2D data. Clearly, there is no way a line can simply separate it.
Manish, I think you are still on the old screen.
Wait, my slide moved forward. So new share. I think okay, I have to reshare. Okay, got it. Yeah, I think now it's a slides now, right?
Yes.
You guys can see the kernels slide now, right? Yeah.
Yes.
Yeah. So yeah, as I was saying, again, since it's in a 2D, there is no way on the left image. There is no way a single line can separate this data, right? So what we do, we just like some hypothetically and mathematically port this data to a higher dimension. So this is one example of porting it to a polynomial, like 3D dimension in a polynomial using a polynomial kernel. Again, if we see, okay, this is not just not separable in a polynomial dimension, we will apply some other fancy kernel. We will make it to a some extra high dimension. We can do that. Keep on doing until unless it may not always be possible, but you at least keep on experimenting till you are satisfied. Okay, this is eventually not separable, but there is still a chance if it's not separable in a 3D dimension using a hyper. Now, yeah, now if you see this red and blue is once you put in this dimension, it's now separable using this plane. Now, if again it's not separable in this 3 dimension, you may try to add different kernel, maybe use a radial kernel. Radial is like a spiral shaped kernel you put in the n dimension. Maybe in that dimension it might be able to differentiate for you. A single plane of n-1 dimension can be able to differentiate 2 classes. And again, now it's I'm taking 2 classes because, and after 2 increase, if their classes increase, you again go back to 1 versus all or 1 versus 1 strategy. So that's the kernel trick that we use. So let's, I think I'll cover the features first, then I'll go through the demos. So now I'm covering one feature. There are many features you can do. Now, as I mentioned, it's an image, right? Image is eventually a list of numbers that in the very first slide I was talking about some voodoo you do with the numbers. This is the voodoo that you do with the numbers. Now, if you look at this square image, every pixel will be some value, intensity value. I'm talking about, say, just don't imagine multiple channels or something. Just imagine single value. Say of this red portion block, this is the value of these numbers.
Manish,
yes.
Before you go forward, Muskan is asking, could you please explain kernel in a little bit more detail? Like what is kernel? I think that bit got. Okay.
So, Muskan, so kernel is nothing, just a transformation that you apply on the input data. So if you see here, right, if I'm talking about a polynomial kernel, so earlier my data was x1 and x2, right? But I know I can't separate it in this 2D plane. What I did, I applied this square kernel. That's called a polynomial kernel for me. I applied I made my feature, I changed my feature x1 and x2 to my new feature became x1 square and x2 square. So this is like one example of kernel. If you can apply more kernels, it's just a sort of a transformation that you do to port your whole data from one dimension to another dimension. And typically in case of SVMs, we do to like a shift from like a lower dimension to a higher dimension, so we can check if that data is separable and going in some other dimension. Think of it this way. Say you are playing on the ground with some balls, okay, red balls and blue balls. Now those balls are scattered around. You were like a good kid, you keep them separated. At about that point, you can just put a stick between those two balls, and you can simply put a line or a stick between it. Like someone came, he kicked the balls. Now balls are all mixed up. Then you can't separate those balls. So what you do, at some point you try to throw these balls into the air, and at some point with your cool ninja skills, you're super fast. At some point you see, okay, at this moment balls are now separatable in 3D space. You put a sheet between those balls, from the red balls to blue balls, to separate. And then once these things are separated, you take a snapshot, and then you try to, using the kernel inverse, you try to get all the details back into the 2D dimension, how that kernel will look. For this, let me share one cool video actually. I think I have a link with that. Okay, let me share that with you. I think I stored a link as well somewhere. Yeah. Yep.
It's fine. You can send
It's a
me.
very simple, small video. Let me just. Yeah, it's a like very cool, like 40 seconds video. You guys are
Okay.
able to see YouTube, right?
Yes, I don't know if the audio will come though.
No, there's no need for audio. It's like a 40-second with just a visualization how kernels work. So see, this blue you see in the circle, in this lined like a sparkling circle, the blue dots. It's a like very blurred, but it's a good visualization of this. And outside, it's a like a greenish dots. And this is your 2D plane currently. Now that's the text also says the blue and red dots, although you are able to see it as a green, the blue and red dots are not linearly separable. Now what we will do, using a polynomial kernel, they can be linearly separated in a 3D space. Now see the transformation. So this whole transformation you're seeing right now, balls are rising up. This is applying your kernel to these balls. Now you see all your features, these red ones and blue ones, they are eventually a feature in 2D, right? Now you applied a kernel, they got transformed into this. You made x1, each value of x1, you made it as a x1 square. So now you see all these planes, this plane now is a linearly, in this dimension it's separable now. But your job is not done, kernel job. What you will do now, you have separated in a 3D dimension, but your actual data is still in 2D dimension, right? What you will do, you'll do the inverse and come back down to the 2 dimension. That's how so that's how you got this circle, because no way in a 2D dimension with the SVM standard definition you could have come up with a circle, right? That's how you come up with this circle from the higher dimension concept.
So basically, from a straight line, you're coming to a curved line, correct?
It's eventually, if you see it in like a crude terms, eventually yes, but saying it's a curved line does not come up with the definition of a SVM. SVM is still called a linear binary classifier. So that's why there are, like these, you can call, in our industry terms, you call these hex, right?
Okay.
So that's but now they have been published like 50-60 years back, they become like a standard research.
So basically, if it is more than 2D, it has to be a curved line. It cannot be a straight line.
Yeah, so it can't be, because eventually you have to port your because your original data is in 2D dimension, right? If whatever dimension you're starting with, you can start with n dimensions, that's fine. But we are talking about like a very baby example. You are starting with a 2 dimension. So the only thing is, if you are starting say with a 3 dimension, you will eventually you have to come down back to that dimension, right?
Correct.
So in 3 dimension, your linear separation will be a plane. This like this is square plane. You can't fold this plane in 3 dimension directly.
Sure.
In 4 dimension, you can't visualize it like with the images, but if you think about like whatever is the linear plane in that will be your classifier.
Fine. Okay, thank you.
And
okay, I have a kind of a basic question probably.
Yeah.
So you can't have non-linear classifiers, is it like ellipse or something?
You can have. So there are SVM is just a starting point. And once you reach convolution neural networks, you can go in anything. You can do anything. You can even do like a 2 separate circles. You can even draw a Mickey Mouse shaped classifier. That's convolution neural network will internally learn. This is like a standard SVM started with a linear binary classifier. That's the introduction to that. That's how this kernel hack or trick came into picture. They even in this standard in this era they call it a kernel trick. They don't call it as like a kernel based or some fancy like a research based term. They still call it a trick.
Okay, so this won't be required once you go to CNNs and things like that.
Yes, so there is SVM. There are other sorts of complex classifiers. There are like Gaussian mixture based classifiers you can use. There are all sorts of classifiers you can use. They take care of linearity. Now in SVMs you are using kernel trick to introduce non-linearity. In CNNs you use this ReLU and all sorts of activation functions to introduce non-linearity. In Gaussian mixtures you use different sizes of different mu sigma parameters to introduce non-linearity. So yes, you can.
Okay, thanks.
So is it safe to say it's a tool to help you? It's a transformational tool to help you visualize something at a lower order in a higher order and bring it back to a lower order, to your original
Not,
order.
I won't say to visualize. So what we eventually trying to do is, see, SVM, as I mentioned, it's again it's still a linear classifier. Linear doesn't mean it is a linear in 2 dimension. It is a linear in n dimension. Now we know, like, it's a standard problem. We know ki eventually, see, you are not interested in getting a single line. You are interested in getting a classifier, whatever shaped, right? You are interested in getting a classifier, whatever shaped.
Yeah.
So we are trying SVM. Why it's still in use? SVM is still one of the fastest classifiers to train and do the prediction from. Other classifiers, they come at a cost. Still, people still try to, like, if they can reduce the problem to SVM, they try to do that.
No, I'm not asking about SVM. I'm asking about a kernel in general.
Yes. So kernel concept outside SVM doesn't hold make sense.
Okay, got it.
Kanish,
Yeah.
do you think we'll get a better understanding representing kernels as like matrices, like considering them as matrices will give a better understanding of whatever you're trying to suggest here?
Yes, eventually, if you're doing applying it on a feature, if you're applying it on a feature, you can have a 1D matrix. If you're applying on a complete grid, or you're doing a vectorization, you will be placing kernels as a matrices only. You might do it as a matrix
Yeah, that should
multiplication.
take
Yes.
away the question of whether it will be like a curved line or all that, right? That'll again modify according to the dimensions that our data is coming up with, right?
It is in essence, but again, so that's why I'm not saying these things standard, because again, as I mentioned, right, this is a hack and these are still acknowledged as a tricks in the field. So there is no standardized research, or like you won't, if you start searching on Google, okay, R kernels matrix, you won't find any results. But in your intuitive understanding, they behave similar way. They are not same, but they behave similarly. How you are going to apply matrix multiplication and all.
Got it. Got it. Thank you.
Yeah. So eventual one line definition is, you get data, you using some kernel, you push it into higher dimension and see if that data is linearly separable in that dimension, in that higher dimension. If it is, do the separator and apply kernel, like inverse kernel, on the separator plane that you find out in that n dimension, so that you reduce the whatever n dimensional plane back to your original dimension. But eventually, if you think about it, it's just a kernel multiplication and then doing a kernel inverse multiplication, right? Matrix multiplication.
Yeah.
Yeah, we can move on.
Yeah. And whoever originally asked that question, is she clear on this?
I'm sure not, but I think it's enough of material to actually go back and read it a little bit more.
Yeah. So I think whoever still has doubt, I think then instead of reading won't make sense. You start to implement with Python. That actually gonna clarify once you see the numbers, like how the number is getting changed. That's my like 2 cents on this. Kernels is a concept you can't, if you are either you build the intuition, or you don't. It's like a very black and white thing. If you don't build the intuition, only solution is go back, implement, and see how the numbers are changing, because any amount of reading is not going to help on this if you are not able to build the intuition. Yeah. So yeah, now moving on to the hawk features. I'll cover the demo part later, but now first I'm covering the hawk features. Hawk features I'm covering because it's easy to show the calculations, because shift, there are sub features, all sorts. So over a period of time, people have tried to make features. Now see, try to make features color invariant, size invariant, space invariant, and all sorts of invariances they have tried to introduce. Hog was one of the early features that did not introduce all those things, but yeah, it's still it's still good enough and still easy enough to understand from that perspective. Hog, as it suggests, a histogram of oriented gradients. Now, if you look, this is the original image from black, there is a black circle, black border. If you put it as a numbers, right? So what you will see, white will be 255 value, right? Black will be 0 value. Your value is like reducing sort of. You're going from black to white. If once you move in horizontal direction, it's called horizontal. You check from vertical direction, you call it a vertical gradient. So moving from dark to light, basically from 0 to 255, you get a positive gradient. Basically your intensity value is increasing, pixel intensity value. From opposite is like that can be positive horizontal gradient or positive vertical gradient. To take an example, let's consider this pixel around it. Say the one that I have marked it as a like a reddish. Say this is a 3 cross 3 pixel inside it, and these are the values. This is your current x pixel that you are talking about, and the neighboring intensity pixel is these ones. These are random numbers. Don't go with the colors combination. Random numbers. Now what's gonna be the horizontal gradient for this? If you move in this direction, 100 minus 20 is your horizontal gradient. That's basically the pixel value that's changing intensity for a gray image. Vertical, 110 minus 50, 60 is your vertical. Now when you talk about gradients, so gradients is a vector, like, so there are two things that define it, right? For a vector, magnitude and angle, right? So how we calculate magnitude? Simply like a square root of sum, so like 80 pixel, this becomes our feature 100 36.86. Now what we do is in this image currently there are 64 vectors, 64 images, right? So you will get 64 such vectors, but now this is just a 8 cross 8 image. But say talk about, you're talking about 1080p, you can't that will become too long of a feature vector, right? So what we do, we just bin them. Binning means like you divide it into some x bins, and you put, say if the magnitude and angle combination is between this to this, it goes into this bin. Magnitude is between this to this, it goes into this bin. Why we are talking about 9 bins? This has been picked from the standard HOG paper, and this has worked and served pretty well for us for everywhere in the industry. So that has, no one has sort of questioned it. They can, if it doesn't, they just experimented, but standard is like a already pretty good site for this, so no one tried to change the standard for this. So eventually if you look each image, now what we do, divide it into some grid, some 64 64 128 128. If you see, like, it will eventually become like a grid of arrows, like 9 arrows. If it's a 9 bins, it will become a grid of 9 arrows. So eventually your hog, okay, it's a sort of, sorry, it's a blur, it blurred out after I didn't notice, but it's eventually like this blurriness, whatever white is, it's like a 9 arrows pointing in all sorts of directions, and the center is the pixel that you have calculated around that box, that the 64 cross 64 box. So what you will be doing, say this is your car image, you will be doing a some whatever size you pick, 64 cross 64, 8 cross 8, you will be doing a sliding window, and in that window, using this calculation, you will be calculating gradients. And say this is your, if it's a 8 cross 8 window that you are sliding, you will divide that 8 cross 8 window into now 9 wins. If it's a 64 64 window, that will become around something 3600 vectors. Again, you will win them into 9 bins. So eventually, once you map it up, it will look something like this, like each vector will have an angle and some magnitude where it's pointing. Does this make sense?
Yeah.
So yeah, so now I'll quickly go into the demo part for this. So again, as I said, I'm not running it, but I have already run these things. So again, these are the pretty cool libraries: skmaze, sklearn, SVM, since it's been standard. There is a great search method as well. So here you set our kernel. I'm just testing with the linear kernel. Now you go into RBF. RBF is a polynomial kernel. You get other parameters as well. You keep parameters, and C is something that we call sorry, I'm blacking out some. Let me think that. It's like a controller based off like the strength of the weights, how you want to divide the weight. To give you an example, say you have 4 boxes. Say you have 4 cups of coffee, and you eventually say want to put 4 coins. One way is to put 1 coin into each. Other is you put 4 coins into one, and like one anything. It's like a combination I'm talking about. But when it comes to machine learning, you always try to, but what will happen, like all these 3 cups went empty, so these 3 cups become our weights that we try to train whenever we are trying to train a model. And empty cup means they are gonna be inactive cups, right? They are not gonna be useful at all if those weights are inactive. So that's what you try to do. If it's like your weights is like simply a linear combination, you will try to spread out the weights. This C factor is the one that actually controls it, like how much weightage you want to give to weights, depending on the back propagation as far as you keep moving. So this is like a grid search. So I think I'll skip this part. I'll still quickly go over this. This is just implementation wise. sklearn is the library that I'm using now. Yeah, train SVM. So very first thing I'm doing is defining the model. Okay, that this you can define later. Define your model, train SVM based on this, based on your parameters. You generate your data. If you go to generate data, what I'm doing here is very first iteration that I've defined two types of feature engineering. What I want to do, feature type, none or hog features. Feature type none, if you look, I'm just reading the image and just flattening it. Simply just passing the each number. If it's a 8x8 image, I'm just passing a vector, a flattened vector of a 64 length. If it's a hog feature type defined, I'll be extracting out the hog features. Now to cover this simple one, you generate same transformations you will apply on your test data. You fit your model. With SVM, the thing is you have already, since I have already defined this as a grid search parameters, now I'm passing this SVC parameter that SVM I have defined to inside this grid and training. It will automatically train with all these parameters one by one, and whichever model performs good, it will automatically just return the final model to me after training. And if you want to even get more insight, like how you want to get independent values for your experiment purpose, you can like one by one set these values inside this function svc. What's your C value? This function takes values of C and all internally. You can provide one value each value at a time. What's the value of C, what's the value of kernel you're going to experiment with. You experiment with, again you will get some numbers. You are not happy, you will rerun with those numbers. You will try with some other combination that this grid search is already doing. So why am this flattening, maybe sometimes it makes sound intuitive, okay let's just try, but why I'm trying this flattening is, even though there was standard hog and all, this was the very first model that I actually trained. When I started with computer vision, I had no knowledge what the neural network is. I heard okay there are terms called hog and sift, but it was at the time I wasn't called, it was too hard of a concept for me to understand. So I was like, I see numbers, I'll just pass all those numbers into the SVM and see whatever it's learning from the direct seeing those numbers, whatever the image is. So you see like these are the numbers. If you see this gray line, so this is a confusion matrix for any classification problem. So this means on the left is the actual class, on the down it's a predicted class. So if you see like 17 images which were actually of the class 0, and if we see class 0 is horsey. So model out of this, it's so how many images are there? 17 plus 1 plus 2, around like 30 images are there. Out of those 30, it's in the 17 times it is saying okay it's a horsey, which means model is not just doing coin flip. So can you tell like what's gonna be if it's a random models probability, what's gonna be the random models probability for this classifier, for this class, 10 classes?
You mean what? The probability number?
Yes. So if you say your model is a random classifier,
Okay.
it just sees an image and randomly puts into a bucket.
Okay.
So what's gonna be the model's probability or average precision for all classes?
50%.
It's a 10 class, so it's a for 2 class it will be 50%. It's a 10 class, it will be 1 by 10, so 0.1, 10%, right?
Yep.
Yeah. So 10%. Now we already see. So if it's a 2 class, 50% is the correct answer. It will just flip a coin. Now it's a 10 class. Every bin gets a 1 by 10th probability. So it will just with the 10% each class, it's gonna be average percent 10. So now we already see we are already at 67% directly, just passing the images. So this is why I'm focusing on it, because other iterations see due to the limitation I have not done much experimentation, but with features you spend more time. So this becomes basically a benchmark for some sense. If you are doing it in a production setting where you have to actually get a good model out, this should become your benchmark for your image classification, that any other model, any other improved libraries or any other convolution neural networks you're going to use in future, you should provide bare minimum this limit for you. Now we'll go with second hog. So hog features is simply again this CV2 OpenCV libraries, they directly provide whatever I explained in the hog feature, how you're gonna calculate. You pass each image, you pass it. And again, orientation is the number of bins. So that's how it's again gonna calculate your hawk feature and list, give you a complete like a list, orientation list for those 9 bins. So this is a model trained for hawk features. Now here you see again, it's although it's good than random, but it's worse than our this normal just a flattened image classifier. Now some of you might have questions like why is it happening, like now we are using some more advanced features. So see, using advanced features, one limitation I mentioned, I do not get much time. I might have hit this one, or I might have even worsened it this one, like using with the default settings. I might have even gotten the worst with if I do experimentation. One thing comes with this more difficult features is like there are issues called overfitting, underfitting. Overfitting is in your training data, you fine tune it so much, your model, that outside that word it does not see any. It's like a blind sighting something. It's like a horse you put around two eye patches around, right? It just sees it straight. So that's what you do to your model. You just put some sort of blank. Okay, it will recognize only if you pass the exact same image, but it won't recognize any new image. This thing in fact I'll cover in the CNN. I'll give you an example as well how it's happening, why it's happening. So again, if you experiment with say shift features or the good images, good resolution images, maybe these features will keep on adding to the value. They can cross the 64, and if you maybe spend time enough and if your features are good enough, you may even hit 100% of all these things. So I'm not focusing much on the metrics part as for now, because that's a completely big domain and that becomes a quite lot confusing. So I'm just using the terms precision. I'm going to explain just precision recall terms here. Other terms are quite confusing as many definitions get added. So precision is something, say your model, say there are like 50 images, and out of those 50, they say there are 50 bird images, say, and your model, out of those 50, there are 25 bird images and 25 animal images. So your model said, say 30 images it said as bird. So in that 30 images, actually 20 images of the birds were actual birds and 10 were animals that it called as bird. So your precision becomes 20 by 30. How many images model actually said as is a bird, and how many of those were actually the bird. That becomes a precision of the model. So that actually tells basically how good your model is at classifying that actual instance. Like it's telling, okay, whenever it's saying bird, it's actually a bird. Then it's a other thing is recall. Now out of those 25, your model didn't say bird for 5 of those images. It correctly classified 20. It didn't say that 5 of them were bird. Your recall, it basically missed 5 of those images. So your recall becomes 20 over 25, which means like 4 by 5, 80% of the times it's able to get your data, but it will miss 20% of the data. So these terms in bird and animal may not make like sound okay, these are pretty important things, but say think about this way. Say you have a very expensive drone, like now we are into some super high tech advanced feature, everyone is using self-controlled drones, and it's like a pretty expensive drone is like gonna be expensive if one drone crashes. So you would try to avoid collisions with other drone. Now your drone detected there is a drone in front of you or not. If some whatever is snapshot is taken in front of you, whether it wants to predict whether it's a drone in front or not to avoid the collision or change course. What would you prefer this drone should have, high precision or high recall? So very first thing, everyone is clear on at least on the definition of precision recall, and if yes, then what would you prefer like your drone should have, high precision or high recall in that case?
Higher recall, right?
Why?
Because it shouldn't miss stuff. I mean, like based on your definition, it shouldn't. It can be less accurate, but it shouldn't completely ignore it if it is in front of it.
Yes. For drone case, yes, that's the correct explanation. You wouldn't want it to crash. It should say false alerts. Okay, it should say that a normal air is a drone. That's fine to avoid collisions, but it should not say whenever there's a drone, it should not say there is not a drone. And then a new other scenarios comes is say spam is also recalled for say healthcare industries. Healthcare industries are the one where say you are spotting like a cancer cells into an image. In that industry, you would prefer your tool's precision is good. It may say, okay, this is not a cancer cell, maybe leave it in a body. That's good instead of damaging some other organ.
In
saying,
health
okay,
industry, you would expect both to be of equal
eventually, yeah. So see, the thing is, eventually you would want that, but precision and, yeah, that's one good and complicated thing. Precision
importance.
and recall, let me share this. They come as a trade-off.
Okay.
So I'll share my sketchpad again once. New share sketchpad. You guys are able to see the sketchpad now, right?
No, not yet. Yes.
Yeah. So precision recall curve, always whenever you're gonna plot for any classifier, precision recall comes something like this. Say this is your recall, this is your precision. So eventually, so your this square box dotted one is your perfect 0, 100, or 1, whatever, or 100. This point is your perfect point. But say your model's precision recall curve is like this. Are you seeing what's happening there? If you try to increase precision, recall is gonna go down. If you're trying to increase recall, precision is gonna go down.
Right. Right.
Until unless, and that's a very feasible model. You can't always get a model that's along this line. So once you have, say, that's what people use, like a precision recall curve to compare two models. Out of these two models, blue one is obviously better. So then you will try to fiddle with the blue one. But once say you are stuck with the blue model, you don't have any update that goes up. You have to choose an operating point now, right? So in your case, when you want higher recall, you would try to get as good as precision. You will try to optimize what we say in standard terminology, that you want higher recall, getting as much as good precision you can get. So you will have a some like fixed recall. Say if your requirement is I want 90% recall, only you are left with this choice only. You have to see like how much good precision you can get, how much model training and all those things you can get your model up. But 90% is your cutoff. You can't afford to have a less than 90% recall. Same thing with precision. You want 100% precision or 95% precision, you are stuck say around somewhere this point.
Got it.
So this is a trade-off. Until unless if you eventually hit this model, another fun fact but like a scary fact, if you hit this model, right, someone said, okay, I got a data set, I'm hitting this model which is going this, it's again not a perfect model. What's the next thing comes in? Then your data is like obsolete. You need to get a new data set because your data,
Correct.
that's never gonna enough live field, especially in live fields. There's never gonna be anything that your model has not seen, that model has seen. That you can't at any point say that my model has seen everything and trained on everything that is there to train on in the world. So once you try to reach, you basically in the production environment, you change your data, you update your data set or add more details to that.
Got it.
So hopefully this SVM part, if anyone has doubt, we are closing the SVM part. Now we'll be moving towards the CNN. So if anyone has slides, now slides are visible, right? Back. Yeah, share slides are there. So if anyone has doubts on the SVM part, please put through. So we'll be stopping on the SVM after this. Okay, so I think I'm not, is there anything? Yeah, so I'll move towards CNN now. So now again, when do you decide that SVM is not enough or some low dimension classifier is not enough, that you need to go into big things? Very good focus. Every data scientist, like data scientist, machine learning engineer, even a normal engineer who is working with any sort of data, very thing that is forced to him to, like, he is encouraged to do is visualize the data, understand the data, what your data is. Because half of the problems, what model you need to do, what feature you need to extract, data tells the story. Every data has its own story. Every data has its own language. Visualize the data. There are tools. If it's a high dimensional data, you use TSNE or PCA to do some dimensionality reduction. PCA like eigenvectors and all, if you have heard that maths. So you do it, you try to plot it, and if you see, like, right, this is it starts with some like hodgepodge data. You do all sorts of PCA reduction. Now you see these clusters become separable. This is a digits data set, which means SVM should be able to work decently well on this sort of data set. Not always you will get this clean cluster. It might be like whatever it was in the start, it might be left at that as well. At that point, you can't do anything. You have to go to some higher convolution neural networks. So that's where now this cool thing came into. So now a story about convolution networks. I think before they came into existence, early existence was like quite long, but they didn't catch up because there was basically due to processing powers we didn't possess. So convolution networks at this point are at such a level, you just give them more data, they will keep on improving. So if people have heard about this GPT-3 that Elon Musk, OpenAI has published, that has been trained on 45 TB of data, around like some millions of books and Wikipedia corpuses, that has been trained for around like over a month's period of time. If you have that much resources, convolution neural network is a blindly just go for convolution neural networks and convolution neural networks. You don't even have to think about SVM. Until unless you don't have those many resources, you still should start from the SVM and lower models. So let's go about convolution neural networks. As the name suggests, main uh, do I have to cover neural networks by the way for anyone? Uh, should I just move to convolution neural networks directly?
I think that will be a separate session, Ganesh. Like,
Yeah, because yeah, that will be some that will be good with mathematical examples now. So I'll go with convolution neural networks. So how this works is like a you directly instead of now till this point we were doing image unwrapping it, doing some hog
one
and all.
one interjection, sorry.
Yeah,
So what now we'll do is we'll assume knowledge on some of these matters, okay? And
yes,
it's a horrible way to do it, but we'll assume knowledge, and what we'll have you do is have another session covering in the missing bits. Like
sure.
effectively, it'd be like missing link dot uh, py for this, okay?
Yes, yes, I know because and I would encourage everyone to put in all the doubts because I know there will be way too many topics. As once I say kernels might not be clear, I try to get more cool mathematical examples and all. So yeah, that can be done. Yeah, that will be great. Yeah, just pitch in all those things that people are confusing. So yeah, let's move forward with this. So convolutional data networks till this point, as we were saying, we were doing seeing the numbers and then doing some manipulation and then doing it. So what maybe people's came in people's mind is like, why are we doing all this mathematical stuff? We don't want to do that. We have had enough of our maths in our like whole school. We just it's an image. We are seeing an image. Computers should also directly see an image. So what we do is we build a pipeline and architectures or in all the libraries like that. You directly throw in an image. You don't have to worry about what its intensity is, what's it, all those sorts of things are. You define like a number of processings you want to do. So you know, like as I mentioned, you will be doing hog features, you will be doing shift features, you will be doing all sorts of channels, color channel differentiation. What you do here is you define for an image, you will set a number in your model architecture. Okay, give me 50 different processings. Your model will learn eventually as it goes to and fro, does some back propagation and everything. It will eventually learn what those 50 pre-processings are gonna be. Some of those pre-processings may simply correspond to a hog feature. Some of those may simply correspond to shift feature. Some of them maybe like how you design architecture, they just correspond to a direct image as well. But computer network will itself take care of it. You don't have to worry about it anymore. All you have to worry about how many processing you want, and that feature you have to set after again doing some bit of to and fro. So if you see like quickly, like here is a one single image, you pass it here, it does some you this number of 3 channels, this is your first layer of number of processings that we call output channels. How many channels you want, you will do some of this pooling and relu voodoo, I'll again explain afterwards. You do some this, again you do some convolution. In first convolution you created 3, you will do again new convolution, you will make more channels, again you will do pooling, you will do some sort of different layers. Fully connected layers is something where every point in this pooling layer of whatever previous layer is connected to the every point in the next layer. So there are very deep they are very, it's like a, so convolution networks to help you build intuitions, like if people are having doubts, to help you build intuitions how this industry convolution neural network and same similarly for parallel natural language processing industry works. People play around with it, people will break connection, people will change settings of these all those settings, and then if it works out, then they'll find an explanation. Okay, why did this work? In other things you will think first, okay, this might work, let's do changes according to that thought process. Okay, and then see if it's working or not. Here someone feels like, okay, instead of 3 I'll have 50 convolutions, instead of this relu I'll define my own activation function. I don't like this pooling that people are doing. or instead of this fully connected, I'll define like 30 connected layer, that I'll connect only cherry pick 30 nodes somehow. You do it. If it works, create an explanation, write a research paper for it. So yeah, this is a convolution neural network feature engineering part, how it's taking the features. This is like a very generic label description. So if you are starting with a face image, this first layer is this first layer, I'll also explain what a convolution is, just to assume so far that this is a convolution happening here. Very first level of convolution will extract out all the edges from it. Now again, on those edges images that you have generated from the original image, you again apply convolution. It will learn some mid-level features. Again, you repeat the process, apply some again convolutions, you will get more detailed features. Now here you are seeing like it's exactly generating faces. It may not exactly be a face, but it will learn some descriptive features. Say for a, you are doing a car versus aeroplane, so it will learn, it will start to focus on the features that car has 4 tires, aeroplane doesn't. It will, aeroplane has a wings and a tail, car doesn't. It will learn those sorts of features as you go deep and all. And if you go, say like now, if you see like as a face, if you go deeper, it may also do some sorts of features that for, if you visualize, they will just look like a lighting blob to you. You may not understand, but network understands those values. So lighting blobs, basically whatever you are able to see, right, wherever, okay, this is a recognizable. In this convolution term, we call it a activation. That this eye, here is eye, here you're seeing, okay, this in the feature map you are able to see some eye. This area has this area has activated some pixel around this area. So say for a, say example, a snake versus a, like a, as I mentioned, or simply let's say car versus plane. So for planes, once you do go deep enough, once you start visualizing the internal images, eventually these are all after applying images, they are numbers, but eventually you can convert it to an image anyways, right? So once you internalize and you visualize, you will see for a plane's images, once you pass it through all these layers that you have trained, there is a like a light, like a brightened area around the wings, which means the wings in the plane image model has learned that it should have wings. So that's based on a training data. You can basically change that behavior, but it will learn some feature. It will start to activate that plane's image, activates that area, like plane's image or activates around that area near the wings area. So now to cover the convolutions, what's the convolution? So here what you're seeing is like a convolution size green box that is sliding. That's your kernel, or a convolution kernel that we call specifically here. It can be 3 by 3, it can be 5 by 5. And the one blue one you are seeing, it's a image, actual image. Here you are seeing a 0 1 to just simplify your calculations if you someone wants to do a mental calculation quickly, but values will be typically from 0 to 25 for an image. And these convolution values can be anything. It can be 0 to infinity and continuous values. Typically we try to keep weights between 0 to 1 because you don't want to deal with like very big numbers. Big numbers, storage, your process will slow down everything. You try to keep it between 0 to 1 weights, 0, and it's a continuous value. It can be 0.1, 0.2. So if you see like very first 3 grades, if you see like it's a sliding window, what's happening, each cross multiply not dot multiplication, each corresponding elements get multiplied, and all these 9 values that you are generated, they are put in they are added, and that becomes the value of this. So this is a GIF. I can pause it, sorry, to show the calculation. But if someone has still has doubts, what I can do is I can show it on a scratch pad if someone has doubts. Or should I just skip this? Convolution is understandable.
Skip it for now, I think.
Okay. Now, yeah. So
But-
other main thing that I talked about, activation functions, you guys know. So there
But
have
I'm-
been, yeah.
But I'm going to ask you to explain it at some later point because I have access.
Yeah, time is quite. I knew this might
I'll
happen.
ask you to explain it, and I'll put
Okay.
it out for people to see later on as a side
Sure.
video.
Sure. I'll do that. Yeah. So again, this activation function that I talked about. So there are many activation functions. What activation functions are doing? If you see here in convolution, right, it is eventually a linear combination. And we know like a hard reality with a linear combination, there is a very gonna be a small part of images that you can actually classify. So sigmoid functions, ReLU, tangent functions, you should start to put all sorts of non-linearity. What you will do is on these images, on each value, you will start to apply this function fx. fx currently ReLU is defined as max 0, x. Again, this has been picked up into, there are some issues with training convolution networks, exploding and vanishing gradients, biases, and to solve this, ReLU works better for convolution neural networks. But you can play around with, depending on your user case, you might want to fall back to sigmoid. Sigmoid is basically simply ex upon 1. I think, yeah, e to the power x upon 1 plus e to the power x or e to the minus x. You apply that function on each value of x that you are seeing in this block.
But
Or you may apply simply, yeah.
sorry, Ganesh. But sigmoid is applicable in linear regression, right?
So see, sigmoid is applicable. So what sigmoid does is, what does sigmoid does?
No, I'm asking. So I'm
Yes, so that's the
it's
same sigmoid function. It's
okay.
applicable here as well.
Okay,
No,
okay,
if
fine.
you think about it from a generic point of view, so I'm just trying to explain. What sigmoid does is typically squash any values between 0 to 1.
Correct.
With some introducing, with some, if it's even if it's on a line, it introduces that curved non-linearity, right?
Correct. So what I'm saying is, so that kind of classification goes into a supervised regression kind of a training, and this is
Yes.
the CNN part of it.
Yes. So yeah, that's what I've covered in the very first slide. So if you remember, right here, I said this convolution part. You don't have to worry about what type of training it's happening. You just put in number of channels.
Okay.
By coincidence, it might happen it has learned exact same weights and features that your linear regressor might have learned.
Okay.
So it takes advantage of, so this is a cool thing and like a sort of a magical thing. It can learn anything.
So
because you
there
will
is
be doing so many to and fro passes, and you'll be
okay.
updating weight so many times. You'll be given your GPU processing. It can
Okay.
end up learning simply a linear regressor classifier.
So in the interest of time, I'll just save my other questions later.
Yeah, sure. So again, I'm just repeating this thing. So this CNN is basically, you have just put some model in place, some architecture, but given your data classifier, it may end up simply learning as a Bayesian classifier. It may, given your training hyperparameters all, you can make it whatever depth, you can simply make it learn a normal Bayesian classifier or a random classifier. So you can try all sorts of activation functions to define what sort of nonlinearity you want. So this is the ReLU. It's the latest FAD that has been like working pretty well on higher end stuff, on especially in all those healthcare and all those industries. That's where images basically become to not of rigid objects mostly. So you want some like a different sort of non-linearity to deal with problems that come while training these things. Now, if you're seeing, right, say now we have problems that I'm saying, and why we need sigmoid type functions when I said 0 to 1. So now this is one convolution. Although the values are, it's a sparse matrix, right? And we are applying only 1 0. Now see 4 3 4 values are increasing. Again, if we'll apply convolution, values will increase. You see what's happening? Values will keep on increasing. You need to bring them back. You need to normalize them back. Else, if it keeps on increasing, your some point, if you are having 10 layers of convolution, at some point values will become so large, and it's like a like exponential operation. It will become so large, it will slow down or hang your whole system, or it may like simply not learn anything. It may saturate. So yeah, that's why we can have sigmoid or all sorts of functions. People simply use sine function for fun as well. Just let's apply a simply sine or a cosine function.
Okay.
You can do that. You can play around with that. So yeah, may not work well, but yeah, for fun you can at least experiment. If it solves a problem, again, as I said, you can publish a paper in this if that solves the issue. So again, for CNN, again the part will be similar. 4 steps that I mentioned: data processing, model definition, model training, evaluation. Here I'm using a PyTorch library, and PyTorch and some sort of image handling libraries. Here in PyTorch, the concept is like works as a data loader. So I have defined as a data loader. Data loader is more of a iterator that instead of returning, it sort of yields one by one example when the model needs. So it's just a simply read all images, load it into a memory, apply the transformations that you want. Transformations I'll show in a second. Transformations, yeah, let me show them transformations first. Yeah, so your transformations can be if you see like resizing. Transformation is basically data augmentation. Resize the image, then you crop out. I'm standardizing on 256 2 cross 256. Do that. You want a random horizontal, you want to flip an image, you can do that. Like just flip it. Flipping helps say all your whatever cats and dog are facing in north. So your model should not be biased. Okay, say your data is something like that. All cats are eventually facing north or one direction, left direction. You don't want a model to like start learning ki, okay, whatever is facing left side is a cat, or a cat have to face left. So you do some sort of flipping. And these are some sort of like a generic you need to. And this normalize is basically taking care of the color intensities. Basically, if it's a multiple intensity, same image in multiple intensity, you normalize the intensity behavior. You can do other you can keep adding to this augmentation list as well. Whatever augmentations you feel like, you define your own custom augmentation, add it to the list. This data loader is set such that it will just apply all those augmentations on the image it's reading. It will apply all those augmentations, you return it. Now comes the second part, defining a model. Here I'm using a very basic architecture for convolution neural networks that have been used. So in neural networks, you will come across names. People like to give names to their architecture, whatever starts work for them. LXNet, LaneNet, ResNet, GoogleNet. Everyone likes to keep their names. So this, and that becomes a cool standard in the industry. If you are doing interviews and everywhere, they'll ask, are you using some LXNet, ResNet, and all those things, and then you explain what is that. So here I'm using a LaneNet. LaneNet is nothing but simply it says I'm, instead of like whatever, it's a standardizing the number of convolution layers and the fully connected layers. I'm going to use just 2 convolution layers, and I'm going to use 3 fully connected layers. This becomes my LaneNet. That's how do I go to that? Yeah, that's how my LaneNet looks in, if I put it into image. You get your image. You guys can read the size, right? Image comes as a 3-dimensional image. 32 number is a number of batch size. You, instead of passing a single image, you pass a batch, and the size becomes 256 cross 250. You apply first convolution, your image size changes. Now the pooling operation, what it does is, okay, this will make more sense once I show this. So see, I have run this. Now this transformation is complete. You have loaded this data. Now it's a time to load your model. So now if you load a model, you see, even I have tried to, given my resources, I have tried to minimize it. But you see, these are the number of parameters you're going to train while you're training a CNN. How many is it? It's like one instance. It's like over like 60 lakhs parameters that you have, 6 million parameters you are going to train. And that's very small architecture model with very less values, very small size images I'm going to train. So you can imagine if it's a classes increases or you add one more convolution layers, this thing can go to billions, right? So you have to put in some measures in place, like some sort of a trick in place to keep reducing the size of images as it move forward. Pooling is one such thing. So pooling, what it does is, let me quickly show. Yeah, say I'm defining a 2 cross 2 pooling here. So 2 cross 2 pooling is, it takes a window of size 2 cross 2 and starts sliding across the images. Say the value of this window is 4, 5, 1, 3. So now if I'm defining a max pooling of size 2 cross 2, what it's gonna simply do, pick the max value out of these 4. If I'm defining average pooling, it's gonna take a average 1 plus 4 plus 9, 13 by 4, whatever it's gonna come to 3.25. Now, does anyone know like what this intuitively, can anyone relate what's happening here? So what happened now, for a 4 pixel, I reduced it to a single pixel now. Its value can be 5 or whatever parameter I defined, 3.25. And so eventually what's going to happen, if your image is of size 100 cross 100, you apply this sliding window pooling, your image is going to reduce to a size of 50 cross 50, right?
Yeah.
So yeah, so can anyone like see what's happening? Once you can define other poolings as well, but can anyone see what's happening here exactly when you say I'm applying max pooling, or I'm applying,
the number of layers is reducing.
Number of size of layer, not number of layers, size of layer.
Size of layer.
But say no, what I want intuitively, what is the difference between applying average pooling or max pooling? So okay, here it goes. Simply, average pooling is simply a average of all these are pixel values, right, after some convolution, right? So once you say max pooling,
you're making it blur, or you're increasing the resolution or something.
No. So what I'm saying is, see, eventual goal is to reduce the size of image. Correct. So here what I'm doing is, it's in the sliding window, When I say max pooling, I am saying just pick the pixel with the maximum value. Intuitively, you are picking the pixel which is having a highest effect on this small group. So once you
So
see it in a higher resolution,
it is
like
precision versus accuracy.
no, it's not precision versus accuracy. So see, once you do pooling, you are instead of 4 pixels, now you're gonna see less data. Overall precision might take a hit, but that gets adjusted due to multiple convolution layers. But what you are seeing is, ki say this pixel has been taken around. Say there is a circle. This box has been taken around this something. So your pixel value, if it's a circle passes to this, pixel value will be somewhere around like some colored pixel 5, 1, 2, 3. What you are saying in max pooling is pick a pixel that is having a maximum influence on this small 2x2 group. So that's the 5
Basically, it's
pixel.
So it's the most prominent feature.
Prominent feature,
Can
yes.
we?
Most prominent feature. In average pooling, you are seeing, I don't know, care about prominent features. Just take an average of all those features. You can define a weighted average as well if you want. Weighted average pooling. So here you're picking prominent feature. Here you are playing, just take an average of this. And since it's a small window, whatever hit this is gonna take to reduce this resolution, it's gonna be adjusted due to the size of network. Just doing an image half, you are doing half image, right? It's an exponential reduce in the size. You can do extra processing, like multiple times extra processing in that scope you have created now. So that will be taken into account in some iteration or some propagation, some weight later.
Okay.
Does that make sense, pooling?
Yeah.
Yeah. So here's the pooling part. So now, as I mentioned, see, eventual goal you have to also keep in track. Like you can train up to 6 billion parameters, right? But again, as I mentioned, no one has a like a GPU that can run for a month for free. So you have to control your parameters you can train. For me to train this like a 20 iterations, even I couldn't do fine tune. It took me like 5-10 minutes on a CPU. Imagine if I just increase, like add one, like double the parameters, that will become 20 minutes for me. If I double it, it will end up taking like half an hour one day. So I have to control my parameters as well, by some method. So that's how what you do. Now there's a Adam optimizer. These parts I'm gonna sort of skip because these are more of a mathematical concepts.
Like
Loss.
Slides.
Sorry.
The 6 billion number is from GPT-3 that you're saying, right?
No. So this one is no. Here you can see the Google my Colab notebook, right?
Okay.
Yeah, this is the parameter for my small network.
Okay.
That is trained on I don't know how many billion or trillion of parameters that will go GPT-3.
Okay.
So my data set is like of only 300, 400 images that has been trained on 45 TB of data. So that model has that model is stored on like a cluster, like a whole external cluster.
Yeah.
That's how big that model is eventually in the parameter size. So now coming to these loss and optimizers, I will just give you a generic overview because these are sort of will require mathematical explanation to get more detail. So loss is simply you calculate your first iteration, first epoch we call in terms of CNN, first epoch. Your model said this is a dog with some X% accuracy, but your actual output is a cat. So dog. So now what you will say, okay, you are wrong, and your loss is whatever confidence it should ideally it should have 100% confidence for a cat, right? But it said 80% confidence for a dog and 20% confidence for a cat. Your loss is 80% now. 100 minus 20, you're 80% loss low in your confidence. So that becomes your analogy of loss, not an exact definition. Again, I'm just trying to make it generic, but so that makes sense. It's basically how far is your prediction is from the actual target in this iteration. So that this loss that you have done, you feed it back to the model to say, okay, you are at this much loss. You have to retrain. You have to change your settings now. Same with Adam optimizer. Adam optimizer is something generally we use SGD and Nestrobe. So these are the things that say now, okay, you got a loss. You have learned some weight in your first iteration. How you want to apply that loss onto those weights? Do you just want to do a weighted reduction? Do you want to do some fancy stuff with it? Do you want to apply some other parameters and then you want to update your weights? How you want to do it? That's your optimizer definition. how you want to update your weights. This one is a loss, is a how much you are far from the actual output currently in this iteration. Does that make sense?
Yes.
Yeah. So now it's a train, and these are generic functions to train. How am I going to train? I'm keep loading an image, load my optimizer. I'll do a model prediction. It will have learned some, if model will do some prediction, I'll calculate my loss. How far is my predicted from the actual one? Based on that loss, I'll do optimization steps. These two are like relative steps. You do loss dot backward. So there is a term called back propagation. That's like a backbone of convolution neural networks. So back propagation, what it does eventually is, say very first iteration, you started from your image, you ended up predicting something X, you calculated what the loss is, you pass the loss back around every layer telling, okay, this was the loss when you did the last prediction. So you need to adjust your weights. This layer will adjust your weights and then back propagate the loss to the previous layer, saying, okay, this was your loss coming from your side. This much loss was coming from your side. You need to update your weights, adjust the weights accordingly. And that's the how you are adjusting again comes into the optimizer part, whether you want to add to the weights, whether you want to reduce from the weights, whether you want to halve the weights, how do you want to do it. That comes from the optimizer part. So and similar steps you, and then again this gets repeated until unless you achieve your desired accuracy and all. Then again similar steps for evaluation. So here is like, if you see like a training, first you train a model, you evaluate a model. That's a saving part. So yeah, so now this is a part that I want to see. If you see first iteration, it started with a training loss of 12%, validation loss of 15% when it did a first pass, which means like it's approximately at around like this much loss, 2.7 loss. With 2.7, it treat it as a, I'm using since some standard different function, but treat it as it's at around like 88% loss right now. Since it's a 12% correct, it's 88% at loss. So again, in the next iteration, if you see, loss decreased, accuracy thoda sa kam ho raha hai, but धीरे धीरे accuracy starts to increase now. Loss starts to decrease. You see it hit 40, 50, 70. At some point, if you see, okay, in this iteration, it's still increasing. I've tried to do it niche. Yeah. At some point, you see, till this point, your model trains decently fine, 81 training, and this increases. But at some point, you will see validation accuracy is not increasing now. Even though training accuracy keeps on increasing, 88, 89, 90. Validation accuracy is 92. Validation accuracy is stuck at 66%. So can anyone relate what's happening? I have already told this, covered this, but can anyone know what happened here?
I guess it's overfitting.
Yes, exactly. I gave an analogy like putting a eye patches around a horse. It's just starting to see training data. It's just learning training data. Okay, training data looks like this. It stopped caring about the validation data at some point, because you are again and again you are putting in training data, so it becomes obsessive with the training data at some point. This is called overfitting. You don't want that. So that's where your all these hyper tuning parameters, adding more layers come into picture. So overfitting, why will model overfit? Because it has saturated all the actual learning it can do. Now you're just re-updating the same weights. It can't learn anything new, but you are still forcing it to learn. So what you can do is like add more layers to it, increase more parameters according to your data set. If it's a simple data set, it's simpler data set 2 class, it might underfit, like it will become so biased that it won't even learn for the training data. If it's a model is too complicated, but your class is simply 2 classes, it won't even care. Okay, it will assume that my training data is in some dimension or it's some classes. It won't even learn. In that case, you will see your training accuracy is also stuck at 70%, or training accuracy also starts to come down after hitting some certain point. So that's it for the CNN part. Now, if just quickly this slide. Now, this was, as I mentioned, this was the very first step. I'm sharing the correct screen now, right? Yeah.
Yes, yes.
So this was the very first thing that we do, image classification. It's like you want to start with anything, you have to start with image processing. Now then next step becomes object detection. What is object detection? Image classification is you giving a cropped image, cat watchdog. Image object detection, you give a full frame, You're asking the model to tell where is a cat, where is a dog. Image segmentation, you are asking a model to actually put a mask around your dog shape completely in the whole image. So there are different types of semantic segmentation and all sorts of segmentation. Semantic is like you give us a normal natural view. The model has to tell whether this is a tree, this is a buildings, this is a road. It has to completely lay a mask on those images. And then third is clustering that I mentioned, unsupervised, segregating simply the groups. So, okay, this is one group, this is second group, without actually knowing the labels, which one is a dog or cat, but it just knows this is group one, this is group two. So, and the modules used is for standard machine learning, OpenCV and sklearn. They are pretty solid modules. sklearn, I think they both of these modules have their documentation and tutorials as well on all sorts of different features, on all sorts of what is a SVM, what are other classifiers, what's a clustering is. For deep neural nets, deep learning, for experimentation, for this is specifically for convolution networks. Uh, Cafe, sorry. Other things, PyTorch you can use for NLP as well. PyTorch is good for research purpose. It's easy to understand. It's completely Pythonized. Everything is like a Python function. But one drawback is you can't publish a model into production. It does not allow you to get a production publishable model. It just stores a weight into a simply pickle file or like a raw format. So there comes a Cafe and TensorFlow or like Cafe 2 from Facebook. So, and there are so many libraries are also available that you train your model in Python, store your weights for one time for once, and then you port them to a Cafe model so that you can push it into a production, because those Cafe and all models are easy to load on the edge device and all. And for visualization, it's a Seaborn versus Matplotlib standard. So that's all. Now I'm up for all the questions and doubt. I can start answering.
Okay, so Kanish, that was actually a very awesome talk, and I think I'm very happy with just having had two talks. I thought I was actually a bit, I was thinking, is it okay if we just have a meetup for just two talks? But I'm very happy with how it turned out. Both, thank you, Mahesh and Kanish, both of you. I think in the way you've interacted with people, and I'm sure the audience will also. Agree that it has been a very good set of two talks, and I did not expect it to go for so long, but I suppose topics like these do deserve their time and their space. No pun intended. So Rangaswamy is actually asking some more 2 cents from your side on learning ML. So I'm going to allow this because I think we have a forum with some. Go ahead.
So I think this is the sentence I used when I was submitting this talk as well. I have just whatever touched currently in image processing and machine learning is just the tip of the iceberg. There is so much more and so much advanced things people are doing. Can you imagine like how it's so training a machine learning simply model anywhere from natural language, from computer vision, from normal, even for normal statistical data. It's like growing a baby. Like once it's a small kid infant, it starts to learn cat versus dog, but it can't tell you the breeds of a dog. As it grows up, it sees more types of dog, it starts to differentiate those features. Okay, this is like a bulldog, this is a labrador. Same thing is with your models as well. I'm talking in image processing sense, but same thing applies for everything, natural language processing or a simply SVM on a statistical data. As you add more data, more parameters to it, you are allowing the model to like explore more.
Right. So, I mean, and it's such an intuitive concept, but I think it deserves to be because I mean that's what all machine learning is, right? You're trying to make it more human-like.
Yes. Eventual goal of neural networks, I think that's where people started, that they want neural networks. Definition is standard definition is a machine learning model that tries to mimic a brain. That's the standard definition of neural network. And thing about machine learning is, even though it's been in the field, people are doing so much research, Stanford, all those big companies, Facebook and all, no one can claim, okay, it's been a solved problem. Nothing is a solved problem in machine learning. There is always something new, some new guy will come, okay, or some new research will come that will be a breakthrough every now and then. There are things called GANs, generative adversarial network, where we are actually generating images. Here you are taking actual images and doing something with it. Last year, I think it was IBM who published, you do a scribble random thing, it will turn it into an object. If you are just doing a like a line based scribble of a cat, it will actually turn it into an actual cat. If you're drawing a scenery, it will actually turn it into a scenery. So that's how big, interesting, and fascinating this machine learning computer vision. And same for natural language processing. Like natural language processing, to give you an example, like GPT-3. I still remember when this GPT-3 came out. I spent like 2-3 weekends on this thing just to figure out. It's such a cool thing. You just type a sentence and just select that you want to generate a literature in Shakespearean way. It will give you a whole book of. It will generate basically. It will be completely new book, not picked from nowhere. Just a model trained and learning, putting a new book in front of you in a Shakespearean way. You can do anything. You can make it memes, you can make jokes, everything you can ask for from that model. May not be completely human level, but it's such a big milestone. Now I'm also covering from this point of view, 2 cents from learning machine learning. What I will suggest, my journey has been like a bit reversed, so I faced a bit of difficulties. I would be frank on that. So I would prefer make your maths and basic, these SVMs, hog features, all sort of feature basics is strong. Once your Bayesian classifiers, native, what's a supervised learning, all sorts of classifiers. And with maths, don't learn just from the theories. With maths plus experiment, machine learning is something you should know the math of. You should know how it works in practice. If you're missing any one of it, it's not gonna help you in longer run. Pick one topic, just SVM, read all about it, do all the maths, do like all the maths with your hands, write all the equations that the SVM is following, try to calculate. Don't work for the big image, just do a like a simple number like 1 versus 2 classifier, simply something, create our own vector, play around with, do all the calculations so that you see what exactly is happening. And then once you do it like a couple of times, you will start to develop intuition. Okay, once I start, when I said, right, this convolution is happening, this ReLU is happening, now I can actually, when I actually train these models, I can visualize like what might be happening in there once I apply that convolution. These things that I showed, they may not be the you can see these, right, that face is getting detected in a, you can see almost a face in a high level features. You cannot actually see, but once you have trained enough models, you can actually sort of visualize like what might be happening at this point. Then you support that with your mathematical experience, whether actually that is happening or not. And once both things come into sync, you will definitely get a good model. So I would still say start with there is a very good course on machine learning to get started, Andrew Ng. That's like again a hello word of machine learning. Start with on Coursera. It's I think free. Go for that course. Once you get that, it will at least, it may not make you an expert, you may not understand it, but use that course as a like a content list. That course throws in some all the basics and all the advanced level topics that are there that one needs to learn. Write those things down, and then you can start like one by one checking those things. Okay, I learned about this, I learned about that.
Do
So
you
yeah,
have a
that,
blog?
sorry.
Do you have a blog, Kanishk?
Not much. I just wrote a 1 or 2 blogs. No, I don't have a blog.
Okay, okay. Nice talk. Thank you.
Yeah, thank you so much. Yeah,
Yes.
thank you guys. It was fun giving the talk, but yeah.
Likewise, and all the links that you have mentioned, everything, I'll put it up in a blog post that.
Yeah, so I think I'll share my GitHub link with Abhiram. He can share. So I have tried to put all the links that I have in the slides. You can follow those blogs wherever I put the images and all. So yeah, you can follow those blogs as well.
Awesome. Awesome. So yeah, we have our GitHub as well, Bangpypers ka. So we will link, we'll put up a post and link it to your
Sure.
GitHub.
Yeah,
Right?
definitely. Yep.
Okay, then despite the fact that it's extended longer than I bargained for, I'm
Yeah.
happy with how it's turned out. And again, thank you so much, Mahesh and Kanishk. I don't think we'll have time to do the open house talks that we had planned. But Mahesh, do you want to say a little bit something before we wind up? Not sure if Mahesh is still there.
Hey, sorry, I was on mute. Okay. Yeah. So thanks for the opportunity, Avi. I think it's a good talk. So I think Kanishk, thanks for that CNN. I think it's a pretty huge topic, but you covered it pretty well in the short span of time. That's it. Thanks.
Thank you. Yeah, and
I have for people, I have shared the link in GitHub link, my GitHub link for this repository, slides and notebook. You can
right.
pick it.
So this is what I had put up for an older set of talks. Similarly, we'll be doing something for this session as well. I'll put up the links for all of the talks. Again, thank you all so much. You can reach me on Twitter, and if you have any doubts, so I can be the medium between the speakers as well. If not, I will also provide the links, some contact information to the speakers themselves. So in that same GitHub URL, so that you can reach out to them in case you want to, on mail, of course. So yeah, again, thank you all for attending, and the recording will be made available. See you at the next meetup and workshop. And if you have anything to talk about, like these two people have spoken, please reach out to me or any of the other co-organizers, and we'll be happy to give you a platform. We used to have offline talks where we partnered with hosts and all with other companies. I'm hoping we can get to that soon, so that people can actually get in touch with the companies themselves and know about hiring opportunities from those companies, right? So that's the one thing that we hope to do at some point. I think Mahesh, we hope to have a session at Verizon itself, right, at some point. So let's do it. Thank you. Thank you all. I'm ending it now.
Thanks, everyone.
Thank you. Bye.